One day, a generation ship will save every living thing on Earth. It will carry us to safety before Earth becomes uninhabitable. Not a handful of survivors, not a colony of volunteers, everything. This is not a backup plan. It is the only plan. Because Earth already has an expiration date, we know the deadline. At what point does knowing the deadline stop being terrifying and start being the thing that finally makes us move? If this kind of thinking is what quietly rewires how you see existence, make sure to give this video a like. Now let's get started. Let us begin with the timeline, because most people have the wrong one stored in their heads. In about 5 billion years, the Sun will exhaust its hydrogen fuel, swell into a red giant star, and engulf the inner planets, possibly including Earth. It is a dramatic ending. It shows up in documentaries, in textbooks, in late-night conversations about the ultimate fate of things. But that is not the deadline that worries planetary scientists. The actual deadline is earlier, much earlier. And it comes not from the Sun dying, but from the Sun living and slowly getting more energetic as it does. Stars like our Sun brighten gradually over their lifetimes as helium accumulates in their cores and the fusion process subtly shifts. Research by scientists including Ken Caldeira and James Casting, researchers who have spent careers modeling planetary habitability, suggests that in somewhere between 500 million and 1 billion years, the increasing solar luminosity will push Earth past a critical threshold. As the planet warms, the geological carbon cycle, the long-term process by which carbon dioxide is drawn out of the atmosphere through rock weathering, will strip CO2 levels below the minimum needed to sustain photosynthesis. Without photosynthesis, the base of almost every food chain on Earth collapses. Forests disappear, animals starve. The oceans do not evaporate immediately, but the complex web of life that makes this world what it is unravels completely. This happens not because of pollution, not because of nuclear war, not because of an asteroid impact. It happens because the Sun keeps doing exactly what it has always done, burning, and Earth eventually runs out of the atmospheric chemistry needed to compensate 500 million years. That is the honest estimate for how long complex life is remaining on this planet, assuming nothing intervenes. Now, to be clear, 500 million years is still a span of time so enormous that the human mind genuinely cannot hold it. Modern civilization, agriculture, writing, cities, everything we call history is roughly 10,000 years old. The entirety of recorded human experience fits into 1/50,000th of that remaining window. There is time, breathtaking amounts of it. But here is the insight that changes everything. The solutions to this problem, the engineering projects capable of extending Earth's habitability or relocating life somewhere safer or doing something even more audacious, operate on timescales that match the problem itself. Some of them would require millions of years just to produce measurable results. That means any civilization serious about surviving past this deadline would need to begin planning, building, and thinking across geological time, not just for the next election cycle, not just for the next millennium, across spans of time longer than the entire age of our species. And when you truly reckon with what the physics allows at those scales, you realize that the generation ship of science fiction, a single vessel carrying a few thousand people between stars, is not just impractical. It is almost quaint compared to what becomes possible when you have millions of years and a star's worth of energy to work with. The traditional image of a generation ship is deeply human and deeply poignant. A vast metal cylinder slowly tumbling through the void between stars. Inside, forests grown under artificial light, children born who will never know a natural sky, grandparents who remember departure, grandchildren who will witness arrival, generations of people living and dying inside a machine, bound for a destination none of them chose. It is a beautiful and melancholy concept. It says something true about us, that we carry our worlds with us, that home is not a place but a continuity of people and memory and culture. But it also carries enormous physical limitations that make it extraordinarily difficult to actually build. The mass requirements alone are staggering. To carry enough people to maintain genetic diversity, researchers suggest a minimum of somewhere around 10,000 to 40,000 individuals to avoid inbreeding collapse over long timescales, along with food production, water cycling, atmosphere management, radiation shielding and propulsion. You are looking at a structure of almost incomprehensible scale. And you still have to accelerate all of that mass to a meaningful fraction of the velocity needed to reach another star within a reasonable number of generations. The fuel costs are not just large, they are, under current physics, essentially prohibitive. So a different question has started to emerge in serious scientific literature. It is a question that sounds absurd the first time you hear it, but becomes more reasonable the longer you sit with it. What if you did not build a ship to leave the planet? What if instead you moved the planet, not metaphorically, not as a thought experiment to be dismissed, literally moved the planet along with its star through the galaxy, turning the entire solar system into the generation ship, carrying everything and everyone, leaving nothing behind? This is where stellar engineering enters the picture. And this is where the science gets genuinely extraordinary. In 1987, a Soviet physicist named Leonid Mikhailovich Shkadov published a paper proposing something that sounds impossible and turns out to be merely incredibly difficult. He described a structure now called the Shkadov thruster in his honor, that could, given enough time, use a star's own energy output to propel it through space. The concept is elegant in the way that the best physics often is, simple at its core, staggering in its implications. Every star radiates energy in all directions simultaneously. That energy, photons streaming outward at 300,000 kilometers per second, carries momentum. Normally, because the radiation is symmetrical in every direction, the momentum cancels out and the star stays put. But what if you interrupted that symmetry? What if you placed a massive reflective structure, a mirror, on one side of the star, angled just right so that it reflected the radiation back toward the star's surface and redirected it out the other side? You would create an imbalance. More photons streaming out from one hemisphere than the other, and by Newton's third law, the star would begin to accelerate, slowly, almost imperceptibly, but continuously, in the opposite direction. The structure Shkadov envisioned is called a statite, a portmanteau of static satellite. It is held in position not by orbital mechanics, but by the precise balance between the star's gravity pulling it inward and the star's own radiation pressure pushing it outward. Position it correctly, and it hovers there indefinitely, requiring no fuel, no active propulsion of its own. It is a passive machine that runs purely on stellar output. It would be, in effect, the largest and most long-lasting engine ever conceived. The numbers involved are difficult to absorb. To shift the Sun by even 1 light-year, roughly 9.5 trillion kilometers, using a Shkadov thruster would take somewhere between 1 million and 10 million years, depending on the size and reflectivity of the mirror. The thrust involved is almost comically small compared to the scale of what is being moved. But here is the crucial point. The Sun does not need to move fast. It does not need to outrun anything. It simply needs to move, slowly, persistently, deliberately, away from whatever is making its current neighborhood less hospitable, or toward whatever destination a civilization spanning millions of years has decided to aim for. The solar system would drift through the galaxy like a great ship under a steady breeze, taking everything with it. Every planet, every moon, every ocean, every living thing. You would not be leaving Earth behind, you would be taking it with you. And the Shkadov thruster, moving an entire star through the galaxy, is not the most ambitious concept in the literature. It is not even close to the ceiling of what physicists and cosmologists have seriously proposed when they ask what the ultimate long-term future of a technological civilization actually looks like. There are ideas beyond stellar migration, ideas that involve restructuring the sun itself, ideas that involve harvesting energy at scales that would make the entire surface area of the Earth look like a solar panel the size of a postage stamp. Ideas that involve engineering the fabric of a solar system so completely that nothing about it would be recognizable to anything alive today. And some of those ideas connect directly to a question that has haunted astronomers for decades. If a civilization capable of doing these things exists somewhere in this galaxy, and the mathematics of probability suggests one very well might, why have we not seen any evidence of it? Why is the sky silent? That question has an answer, and the answer is more unsettling than the silence itself. We are just getting started. The next part goes deeper into the structures that could harvest an entire star's energy output, and into a mystery so strange that it changes what we think we know about our place in this galaxy. Do not go anywhere. And I want to mention something that genuinely changed the way I experience all of this. When you spend enough time thinking about nebulae, about gas clouds collapsing into newborn stars, at some point you stop wanting to just read about it. You want to see it, not in a photograph, with your own eyes in real time, under a real sky. The Celestron StarSense Explorer is the telescope I would point anyone toward who is at that exact moment. It uses your smartphone to map the sky above you and guides you, without any prior experience, directly to whatever you want to observe. Saturn's rings, the Andromeda Galaxy, the Orion Nebula, things that the first time you see them with your own eyes produce a feeling no documentary can replicate. There is something that happens in your chest when you realize that the light entering your eye has been traveling toward you for 2.5 million years. You cannot get that from a screen. If you are curious, the link is in the description and pinned on the comments. No experience necessary, just curiosity, and curiosity is exactly what we need right now, because what comes next in this story is genuinely one of the most mind-bending concepts in all of modern astrophysics. So we have established that a civilization with enough time and enough intention could, in principle, use a star's own radiation to slowly push it through the galaxy. The solar system becomes the vessel. Earth stays intact. Life continues. Everything moves together across the slow, dark ocean between stars. But that raises an immediate and deeply practical question. Moving a star requires coordination on a scale that is almost impossible to describe. It requires structures built across millions of kilometers of space. It requires energy, enormous, continuous, reliable energy, not just to build those structures, but to power every other aspect of a civilization operating across geological time. And here is the thing about energy at that scale. You cannot get it from fossil fuels. You cannot get it from wind or tidal forces. You cannot even get it from fusion reactors, as revolutionary as those might seem to us today. At civilizational timescales, there is only one energy source large enough to matter, the star itself. And this is where a concept enters the picture that was first described not in a science fiction novel, but in a 1960 paper by the physicist Freeman Dyson, published in the journal Science. Dyson was thinking about the long-term trajectory of technological civilizations, and he noticed something that seems obvious once you hear it, but that almost nobody had articulated clearly before him. A civilization's energy consumption tends to grow over time, and the only object in any solar system capable of meeting essentially unlimited energy demand is the star at its center. Our sun outputs approximately 3.8 times 10 to the power of 26 watts continuously, every single second. That is more energy than humanity has consumed across its entire history, released over and over again endlessly in every direction into empty space, Dyson asked a simple question: what if you captured it? Not all of it, physics being what it is. Perfect efficiency is never on the table, but a meaningful fraction of it. Enough to power not just a city, not just a planet, but an entire interstellar civilization operating across millions of years. The structure he described, now almost universally called a Dyson sphere, though Dyson himself preferred the term shell or swarm, is a collection of orbiting energy collectors arranged around a star in sufficient density to intercept a significant portion of its output, not necessarily a solid shell, which would be mechanically unstable and require materials that may not exist in sufficient quantities anywhere in the universe, more likely a vast, distributed swarm of independent solar collectors, each in its own orbit, together forming something like a loosely organized cloud of energy-harvesting platforms surrounding the star on all sides. The scale of this is worth sitting with. To build a Dyson swarm around our Sun using the raw materials available in our solar system, primarily from asteroids, from the outer planets, from the asteroid belt, you would need to disassemble a significant fraction of the non-stellar mass of the solar system and reshape it into flat, reflective, orbiting structures. Jupiter alone contains enough mass to construct platforms covering an area many thousands of times larger than the surface of the Earth. The engineering challenges are extraordinary, but crucially, none of them violate known physics. There is no proposed law of nature that says this cannot be done. It is a question of time, energy, and will, and a civilization operating across millions of years has all three in abundance. Now, here is where it connects back to the generation ship idea in a way that is surprisingly direct. A civilization that has built a Dyson swarm around its star has, by definition, already solved most of the engineering problems involved in the Shkadov thruster, the mirror that redirects stellar radiation to push the star through space is not conceptually different from the collectors that intercept that same radiation for energy. They are variations on the same fundamental technology. One harvests the star, the other steers it. A sufficiently advanced civilization would not have to choose between the two. They would build both simultaneously as parts of the same integrated megastructure. The swarm powers the civilization. The thruster moves the system. Everything travels together through the galaxy, sustained by the light of its own captured star. This is what some researchers now call a Class II civilization on the Kardashev scale, a framework proposed by Soviet astrophysicist Nikolai Kardashev in 1964 that ranks civilizations by their total energy consumption. A Class I civilization harnesses all the energy available on its home planet. A Class II harnesses all the energy of its star. A Class III controls the energy output of an entire galaxy. We are, to be generous, somewhere around 0.7 on that scale. We use roughly 2 times 10 to the power of 13 watts globally. The Sun produces roughly 3.8 times 10 to the power of 26 watts. The gap between where we are and a Class II civilization is not just large, it is larger than the gap between a single candle and every electrical device currently running on Earth simultaneously. And yet, the mathematics of exponential growth suggests that a civilization that survives long enough, that does not destroy itself in the messy, dangerous adolescence of acquiring powerful technology, will, almost inevitably, climb that scale, not because it chooses energy for its own sake, but because everything it wants to do, explore, build, compute, communicate, move, requires more of it over time. Which brings us to the question that has sat at the edge of this conversation since the very beginning. The question that Dyson himself recognized the implications of when he published his 1960 paper. If a civilization capable of building these structures exists somewhere in our galaxy, and given that the Milky Way contains somewhere between 100 billion and 400 billion stars, many of them billions of years older than our Sun, it seems statistically unlikely that we are the first to reach this level of technological ambition. Then where is the evidence? A Dyson swarm would be detectable. Not visually, perhaps. You would not see it glowing in the night sky the way a star does, but thermodynamically, it would be unmistakable. Any structure absorbing starlight and using it to do work would release that energy as waste heat, radiating outward in the infrared spectrum, heat that no natural astrophysical process would produce in quite that pattern. Astronomers actually have a term for this. They call it an anomalous infrared excess, and they have been looking for it. In 2015, a star catalogued as KIC 84628552, nicknamed Tabby's star after astronomer Tabby Boyajian, who led the team that first reported its behavior, produced one of the most genuinely puzzling observations in recent astronomical history. The star was dimming, not in the smooth, regular, predictable way that a planet crossing in front of it would cause. It was dimming irregularly, in patterns that no natural explanation has yet fully and satisfyingly accounted for. At one point, over a period of roughly a century, it appeared to have faded by nearly 20% in total brightness. Comets have been proposed, dust clouds, unusual disk geometry. None of these explanations have been universally accepted. Jason Wright, an astronomer at Pennsylvania State University, noted publicly, carefully, scientifically, without sensationalism, that the observed behavior was consistent with what you might expect to see around a star in the early stages of Dyson swarm construction. He was not claiming that was the answer. He was pointing out that it fit, that it was worth taking seriously as a hypothesis alongside the natural explanations. The scientific community has not dismissed it. They have simply not confirmed it either. Tabby's star remains, as of the latest observations, unexplained, and it is not alone. A 2021 survey conducted using data from the Wide-Field Infrared Survey Explorer, the WISE telescope, and the Gaia Space Observatory systematically searched hundreds of thousands of stars for anomalous infrared signatures consistent with partial Dyson sphere construction. The researchers, led by a team including astronomer Matthias Suazo, identified several dozen candidate stars exhibiting exactly this kind of unusual heat signature. None of them have been confirmed as artificial structures, but none of them have been fully explained by natural processes either. We are looking, and the sky is not entirely silent. It is murmuring in ways that we do not yet have the vocabulary to fully interpret. Here is what makes all of this so difficult to sit with. The Fermi paradox, the contradiction between the high probability of intelligent life existing elsewhere in the universe and the complete absence of confirmed contact or detection, assumes that we would recognize a technologically advanced civilization if we encountered evidence of it. But what if we would not? What if the signatures of a Class 2 or Class 3 civilization are so different from anything our instruments were designed to detect, so far outside the conceptual framework we bring to the search, that we have been looking directly at the evidence for decades without understanding what we are seeing? There is a version of this story where the night sky is full of engineering, where the dimming of certain stars, the anomalous infrared readings, the strange periodicities in stellar light curves that no clean natural model explains, where all of it is not mystery, but message, not a transmission in any language we would recognize, just the quiet, thermodynamic exhaust of minds at work on a scale we have not yet learned to imagine. And if that is true, if even one of those candidate stars is what the mathematics suggests it might be, then we are not alone in having asked these questions. We are not the first civilization to look at its own sun and think, what if we could use all of that? We are not the first to realize that the planet beneath our feet, beautiful as it is, has an expiration date, and that the universe is vast enough and physics is generous enough that leaving does not have to mean abandoning everything you love. We would be late arrivals to a conversation that has been going on for longer than our species has existed. That thought should feel humbling, it should feel a little vertiginous, and it should feel, underneath all of that, like the most extraordinary invitation you have ever received, to be curious, to look up, to keep asking, and to understand that every question you have ever had about the cosmos is part of something much larger than yourself. But here is what we have not talked about yet. We have spoken about moving a star, about harvesting its energy, about the possibility that others may have done exactly this. But we have not asked the question that sits beneath all of it, the one that changes the moral and philosophical weight of this entire conversation. If we were to do this, if a future version of humanity were to embark on a project spanning millions of years, slowly steering the sun through the galaxy, who decides, who builds, who sacrifices? And what does it mean to be human across a timescale that dwarfs every civilization, every religion, every story we have ever told about ourselves? That answer is coming, and it is stranger and more human than anything we have covered so far. There is a thought experiment that cosmologists and philosophers of science have been quietly wrestling with for decades, and it goes something like this. Imagine you are alive 1 million years from now, not you specifically, but a being that carries the thread of what we are today, in the same way that you carry the thread of the first humans who looked up at the sky and wondered what those lights were. This being lives inside a solar system that has been moving, slowly and deliberately, through the galaxy for hundreds of thousands of years. The star above them is the same star. The planet beneath their feet is the same planet, older, changed, managed in ways we cannot quite picture, but continuous. There has been no break in the chain of generations, no catastrophic departure, no moment where everything familiar was left behind, and yet nothing about their civilization would be recognizable to you. Not their language, not their social structures, not their relationship to time, to each other, to the cosmos around them. The engineering projects they maintain would be so vast, so deeply woven into the fabric of the solar system that they would not experience them as technology any more than you experience the atmosphere as a machine, even though, in a very real sense, it is one. This is the question that nobody in the generation ship conversation spends enough time on, not the engineering, not the physics, the question of what survives. What it means to carry humanity across a span of time so large that every cultural, biological, and psychological anchor we currently have would dissolve completely. And whether the thing that arrives at the destination or that keeps traveling indefinitely through the dark would still be us in any meaningful sense, it is a question that science alone cannot answer. But science gives us the framework to ask it honestly, and that honesty is worth something. Let us start with biology, because that is where the constraints become most visceral. The human body was not designed for space. That word, designed, is technically wrong, of course. It was shaped by billions of years of evolution for a very specific set of conditions: one, gravity, a particular mixture of atmospheric gases, a radiation environment filtered through a thick magnetic field, and a dense atmosphere, cycles of day and night tied to a 24-hour rotation, seasonal variation, the presence of a vast and complex biosphere providing food, medicine, sensory richness, and a kind of deep biological grounding that we are only beginning to understand scientifically. Remove any one of those conditions and the human body begins to struggle. Remove several of them simultaneously and the problems compound in ways that are not always predictable and not always reversible. We know this not from theory but from direct observation of real human beings in space. Astronauts aboard the International Space Station, a research platform orbiting roughly 400 kilometers above the surface, well within the protective bubble of Earth's magnetic field, experience measurable changes in their physiology after just a few months. Bone density decreases at a rate of roughly 1 to 2% per month in microgravity as the skeletal system adapts to an environment where it no longer needs to support weight. Muscle mass follows a similar trajectory without aggressive countermeasures. Vision can be permanently affected by changes in intracranial pressure caused by fluid shifting toward the head in the absence of gravity. The immune system behaves differently. Cardiovascular function changes, sleep is disrupted, and this is in low Earth orbit, close to home, with regular resupply missions and the constant possibility of emergency return. Now scale that out. Not months in orbit, but generations aboard a structure moving through interstellar space, far from any resupply, far from any rescue, far from the radiation protection that Earth's magnetic field provides. The challenges do not just multiply, they transform into something qualitatively different, not an engineering problem with a known solution, but an open-ended biological experiment conducted on living people across centuries with no control group and no option to stop. And here is where the generation ship concept runs into its most philosophically uncomfortable wall. The people who board such a vessel, if we imagine it as a conventional ship rather than a moving solar system, choose to go. They make a decision, they accept the risk, they sign on, in whatever form consent takes in that future moment, knowing what they are agreeing to. Their children do not, their grandchildren do not. Every generation born aboard the vessel is born into a life they did not select, in an environment they cannot leave, traveling toward a destination they will never see, serving a mission defined entirely by people who are dead before they draw their first breath. There is a philosophical tradition that takes this seriously, that argues, not without force, that bringing a child into an environment of such profound constraint is itself a moral act requiring justification, that the generation ship is in a sense the most extreme version of a question every generation faces. What right do we have to make irreversible decisions on behalf of people who do not yet exist? This is not a fringe concern. Bioethicists and philosophers of science have published on exactly this question. Cameron Smith at Portland State University, who studies population genetics and long-term space colonization, has written extensively about the minimum viable population sizes needed for a multi-generational voyage, the genetics of survival across centuries. His work suggests that to maintain meaningful genetic diversity without dangerous levels of inbreeding, you would need a founding population of not hundreds but tens of thousands of individuals. And those individuals would need to maintain active genetic exchange across many generations, which requires social structures, cultural norms, and institutional frameworks capable of surviving intact across timescales longer than most human civilizations have ever lasted. Rome lasted roughly 1,000 years in its most expansive form. The Han dynasty, one of history's great enduring powers, spanned roughly 4 centuries in its original form. The journey to even the nearest stars, if undertaken at speeds achievable with any propulsion technology currently within the realm of serious scientific proposal, would take thousands of years. A journey not to the nearest star but to a more hospitable stellar neighborhood, picking and choosing destinations across a galactic migration, could take hundreds of thousands. No human institution has ever survived that long. Not one. The oldest continuously operating human organizations, certain religious institutions, certain academic bodies, are measured in hundreds of years, not thousands, and they have changed beyond recognition even across those relatively short time spans. To assume that a social structure capable of managing a generation ship could remain functional, humane, and coherent across thousands of years is not optimism. It is, if we are being honest, a kind of faith, And this is precisely why the moving solar system model, the Shkadov thruster, the Dyson swarm, the entire planet as vessel concept is not just more physically appealing than a conventional generation ship. It is more philosophically defensible because it does not require confinement. It does not require asking anyone to live and die inside a machine. The planet keeps its sky, its oceans, its mountains and its seasons and its depth. The biosphere continues, evolution continues, cultural diversity continues. The sheer scale of the Earth's surface, 510 million square kilometers, means that even a civilization millions of years in the future would have room to be strange, to be varied, to disagree, to forget and rediscover, to be gloriously, chaotically, irreducibly human. You are not packing up life into a bottle, you are moving the ocean itself. But even this picture requires something that we have not yet addressed directly, something that sits beneath the engineering and the biology and the philosophy, like a foundation that either holds or does not. It requires time, enormous, almost incomprehensible amounts of it, and it requires a kind of institutional continuity that has never existed in human history. Not a government, not a religion, not a corporation, not a scientific institution, something new, something that can hold a project across millions of years without losing its purpose, without being corrupted or forgotten or dismantled by the ordinary entropy of human social life. Think about what it would mean to begin construction on a Shkadov thruster today. Not that we could, but imagine. The first generation of builders would spend their entire lives on the foundational engineering, the theoretical refinement, the first tentative steps toward assembling something in space that their instruments could barely detect. They would die before seeing any measurable movement of the sun. Their children would inherit a project whose results they would also never witness. Their grandchildren, their great-grandchildren. 1,000 generations would live and die before the sun had moved far enough in its new direction to matter to anyone living on Earth at that moment. What keeps a project like that alive? What cultural or institutional force is strong enough to survive the ordinary forces of human forgetting, the wars, the revolutions, the philosophical shifts, the moments of collective despair when the project seems pointless because nothing has changed in living memory? There is no precedent for it in human history. The closest analogues, the construction of medieval cathedrals that took centuries to complete, the multi-generational transmission of oral traditions across hundreds of years, are separated from the scale of this challenge by many orders of magnitude. We are not talking about centuries, we are talking about millions of years. More than 3 times the entire span of time that our genus has existed on this planet. And yet, and this is the part that I find genuinely moving, in a way that is hard to articulate, the fact that we can conceive of it matters. The fact that a species that has existed for roughly 300,000 years, that only developed writing 10,000 years ago, that only left the atmosphere for the first time 65 years ago, can sit down and work out the mathematics of moving its own star. That is not nothing. That is, in fact, extraordinary. It suggests that the ceiling of what is possible for minds like ours is not the horizon we can currently see, but something vastly, almost frighteningly further. We are at the very beginning of a story whose later chapters we cannot read, but we are writing them, right now, in the language of physics and curiosity, and the stubborn human refusal to accept that the answer to any question is simply, it cannot be done. And that refusal, that specific, irrational, beautiful refusal, may be the most important thing about us, more important than any technology we have built or will build, because the technology follows from it. The generation ship, in whatever form it ultimately takes, begins not with an engineering blueprint, but with someone looking up at the sky and refusing to accept that what they see is the limit of what is possible. You are doing that right now. By being here, by asking these questions, by following this thread into the dark, you are part of that lineage. You carry something that the builders of cathedrals carried, that the first navigators who pushed their boats beyond the sight of land carried, that every human being who ever looked at the horizon and decided to walk toward it has carried. That continuity is real. It is not metaphorical. It is the most tangible thread running through the entire history of our species. But there is one more piece of this picture that we have not yet placed, and it changes the emotional texture of everything we have discussed so far, because we have been talking about the generation ship as a solution, as humanity's answer to a problem. But there is another way to frame it, a frame that is darker and stranger and ultimately more honest about the nature of the universe we actually live in. The universe is not static. It is not waiting patiently for us to figure out our engineering. It is evolving on its own timescales, in directions that create their own deadlines, deadlines that have nothing to do with the sun getting brighter or the Earth's carbon cycle breaking down. Deadlines that operate at scales so vast they make even the 500 million year estimate for Earth's habitability look like an afternoon. And when you place the generation ship concept inside that larger frame, inside the full, honest, thermodynamic story of where the universe is going, the entire project takes on a different meaning. It stops being about survival. It starts being about something much harder to name, something that sits at the intersection of physics and meaning, and the very strange fact that the universe has produced, at least once, something capable of understanding its own fate. What that means, and what it might require of us, is exactly where we are going next. If you are enjoying this journey, make sure to give this video a like and subscribe. Every video on this channel goes deeper into the cosmos, and you want to be part of this community. There is a concept in physics called the arrow of time. It sounds poetic, and in a way it is, but it describes something very concrete and very unsettling. The laws of physics at the fundamental level are almost entirely symmetrical with respect to time. A film of two billiard balls colliding looks the same whether you play it forward or backward. The equations that govern the interactions of particles do not care which direction time flows. And yet, at the scale of the world we actually experience, time has a very clear direction. Eggs break and do not unbreak. Stars burn and do not unburn. Heat flows from hot objects to cold ones and not the other way around. The universe, taken as a whole, is moving in one direction, from order toward disorder, from concentrated energy toward diffuse energy, from complexity toward simplicity. This is the second law of thermodynamics. And it is, depending on your philosophical disposition, either the most sobering or the most clarifying fact about the nature of reality. What it means, in the longest possible view, is that the universe has a direction. It began roughly 13.8 billion years ago in a state of almost incomprehensible density and temperature, with an enormous reserve of what physicists call low entropy, usable energy, structure, difference. The difference between the hot, dense regions and the cold, empty ones is what drives everything. Every star that burns, every planet that forms, every creature that metabolizes, every thought that forms in a biological brain, all of it is powered by the slow, inexorable flow of the universe from its initial low entropy state toward its final high entropy one. And the final state, the destination that the arrow of time is pointing toward, is called the heat death of the universe. It is not dramatic in the way that a supernova is dramatic. It is the opposite of dramatic. It is the universe reaching a condition of perfect, featureless equilibrium, where every region has the same temperature, where no energy gradients exist anywhere, where no work can be done, no information can be processed, no thought can form. A universe in which nothing happens, because everything that could happen has already happened. and there is no longer any difference between one state and any other. This will not occur for an almost absurdly long time. We are talking about timescales measured in 10 to the power of 100 years or more, numbers so large that the current age of the universe, 13.8 billion years, would not even register as a rounding error. But the direction is fixed, the destination is real. And the implication for everything we have been discussing, for the generation ship, for the Dyson swarm, for the Shkadov thruster, for the entire project of long-term civilizational survival, is profound because it means that there is no permanent solution. There is no engineering project, no matter how vast, that can run forever. The stars will burn out. Every star in the Milky Way, every star in every galaxy we can observe, will eventually exhaust its fuel and go dark, the last ones flickering out somewhere around 100 trillion years from now. After that, the universe will be a cold, dark place populated primarily by black holes, slowly radiating away their mass through a quantum process called Hawking radiation over timescales that beggar description. And eventually, even they will be gone. This is not speculation. It is the straightforward application of well-established physics to the long-term future of the universe. The cosmologist and author Brian Greene has written about it. The physicist Freeman Dyson, the same man who described the energy-harvesting megastructure we discussed earlier, spent considerable time late in his career thinking about what kinds of information processing and what forms of experience might be possible in the very far future of a cooling, darkening universe. His conclusions were characteristically optimistic, but they required accepting a kind of existence so different from biological life as we know it that the word human would barely apply. So here is the question that all of this raises, and it is not a comfortable one. If the universe has a fixed direction, if entropy always increases, if every star will eventually go dark and every structure will eventually dissolve, what is the point of the generation ship? What is the point of the Dyson swarm, of the Shkadov thruster, of any of it? If the destination is heat death regardless, why build, why plan, why move a star? I want to sit with that question for a moment, because I think the instinctive answer, the one that says it is pointless, that nothing matters if it all ends the same way, is not just philosophically unsatisfying. I think it is wrong, and the reason it is wrong tells us something genuinely important about what science reveals when you follow it all the way down. The fact that every candle eventually goes out does not make the light meaningless while it burns. The fact that every person dies does not make a life without value. These are not just comforting platitudes. They reflect something real about the structure of experience and meaning. That value is not located in permanence. It is located in what happens, in the quality and richness and depth of the process itself, regardless of how it ends. A civilization that moves its star is not doing so because it has solved the problem of entropy. It is doing so because the alternative, staying still, accepting the deadline, not trying, forecloses possibilities that staying in motion keeps open. Every million years of continued existence is another million years of experience, discovery, relationship, art, knowledge, and whatever other dimensions of richness a civilization spanning geological time would develop that we currently have no concepts for. The point is not to last forever. The point is to last longer and to use that time well, and to be genuinely, fully alive for every moment of it. There is a phrase that the physicist Richard Feynman used in a slightly different context that has always stayed with me. He said that the universe is not obligated to make sense to us. It operates according to its own rules, on its own scales, without any particular regard for human comfort or human categories. And yet, and this was the thing Feynman found endlessly astonishing, we can understand it, not perfectly, not completely, but meaningfully. We can work out the mathematics of stellar evolution and thermodynamic equilibrium and the long-term fate of galaxies, and those calculations correspond to something real. The universe is legible, and that legibility, the fact that minds like ours can read the universe's story, even the parts that are uncomfortable, even the parts that end badly, is one of the most extraordinary facts about existence. We are, as the astronomer Carl Sagan said, the universe knowing itself. Stars that have lived and died contributed the carbon in your body, the oxygen in your lungs, the iron in your blood. You are not separate from the cosmos looking at it through a window. You are a part of it that has become sufficiently organized to look back at the whole. And when you think about the generation ship, when you trace the logic from a brightening sun to a Shkadov thruster to a Dyson swarm to a civilization moving through the galaxy across millions of years, you are not thinking about an abstract engineering problem. You are thinking about what the universe does when it produces something curious enough to care about its own future. That is not a small thing. That might be one of the most remarkable things in the known universe. Now there is a dimension of this conversation that we have been circling without landing on directly, and it involves a discovery so recent and so significant that its full implications are still being worked out by researchers around the world. In 1998, two independent teams of astronomers, one led by Saul Perlmutter at Lawrence Berkeley National Laboratory, the other led by Brian Schmidt and Adam Rias at the High-Z Supernova Search Team, made an observation that stunned the physics community. They were studying distant supernovae, using them as standard candles to measure the expansion of the universe, and what they found was not what anyone expected. The universe was not just expanding, it was accelerating. Something was pushing it apart faster and faster, overcoming gravity at the largest scales, driving galaxies away from each other at increasing speed. That something has a name, dark energy, and beyond the name, we understand almost nothing about it. It constitutes roughly 68% of the total energy content of the observable universe. It is everywhere. It does not dilute as the universe expands, and its effect over truly vast timescale is to pull the observable universe apart until the galaxies beyond our local group, the cluster of roughly 50 to 80 galaxies gravitationally bound to the Milky Way, will recede beyond the cosmic horizon entirely. In roughly 150 billion years, any civilization still surviving in the Milky Way will look out at a sky containing only its own galaxy. Everything else will have moved beyond the point where light from it could ever reach them again. The universe is not just running down, it is also pulling apart. The resources available to any future civilization are not static, they are shrinking, in the sense that the matter and energy accessible across cosmic distances is becoming less and less reachable as the expansion accelerates. This makes the long-term project of civilizational survival not just an engineering challenge, but a race, a slow race measured in billions of years, but a race nonetheless, against a universe that is gradually making more and more of itself unreachable. This changes the strategic calculus of the generation ship in a subtle but important way. It suggests that the window for intergalactic expansion for a civilization ambitious enough to think not just about moving within the Milky Way but about reaching other galaxies is not infinite. It is long by human standards, but it is finite. Andromeda, the large spiral galaxy currently on a collision course with the Milky Way, expected to begin merging with us in roughly 4.5 billion years, will remain accessible. The galaxies of the local group will remain bound to us by gravity. But beyond that, the cosmic expansion will eventually win. The rest of the observable universe will become, for all practical purposes, unreachable. And so the generation ship, in its most expansive, most ambitious interpretation, is not just about moving a solar system through our galaxy. It is about deciding, while the decision can still be made, how large you want your future to be, how much of the universe you want to claim as home before the door closes. It is the most consequential real estate decision in the history of anything. A civilization that acts early enough, that begins the project of stellar migration while the universe is still young enough, while other galaxies are still reachable, inherits a cosmos. One that waits too long inherits only its own neighborhood, however vast that neighborhood might be. We are right now at a moment in cosmic history when the universe is still young. The first generation of stars, massive, brilliant, burning fast, have come and gone. But the stars like our sun, the quieter, longer-lived ones, are in their prime. The universe is roughly 13.8 billion years old. The era of star formation will continue for perhaps another trillion years. We are not at the end of the story. We are not even at the middle. We are in the early chapters before the plot has fully revealed itself, at a moment when almost everything is still possible. That is a remarkable place to be. And the choices made in these early chapters by species like us, on planets like this one, may echo in ways that persist across timescales we cannot currently imagine. I want to leave you, before we go any further, with a single image that I think captures something true about all of this. On a clear night, far from city lights, you can look up and see the band of the Milky Way stretching across the sky. What you are seeing is the combined light of roughly 200 to 400 billion stars. Most of them too faint to resolve individually, their light blending into that soft, luminous river. Some of those stars are older than our sun by billions of years. Some of them, statistically, almost certainly host planets. Some of those planets, by the same statistics, have had billions of years more than we have had to develop whatever they were going to develop. And somewhere in that band of light, in that river of ancient fire, there may already be engineering. There may already be structures, decisions, migrations underway that began before our planet had finished forming. There may already be answers to the questions we are only now learning to ask. Or there may not. The silence may be real. We may be the first, or among the first, which would make our choices not just consequential for ourselves, but for the entire future of mind in this galaxy. Either way, whether we are late arrivals to a populated cosmos or pioneers in an empty one, the responsibility is the same: to think clearly, to act wisely across the longest possible timescales, to take seriously the idea that what we do now and what we choose to become matters not just for the people alive today, but for every generation that will ever exist in this solar system. That is not a burden. It is an invitation, and we are just beginning to understand what answering it might actually require of us. There is a field of study that sits at the intersection of astronomy, engineering, and something that might generously be called cosmic archaeology. It does not have a single universally agreed upon name, but researchers working in it sometimes call it astroengineering or megastructure studies, or, in its more speculative but increasingly serious form, the search for technosignatures. And what it asks, at its core, is a question that sounds almost childlike in its simplicity, but turns out to be one of the most scientifically and philosophically loaded questions a human being can sit with. What would a civilization more advanced than ours actually look like from the outside if we were searching the sky for evidence of minds at work on a truly large scale? What would we expect to find? This is not the same question as the search for extraterrestrial intelligence in its traditional form. The traditional form, radio telescopes listening for structured signals, the SETI program scanning frequencies for patterns that nature would not produce, assumes that another civilization would be trying to communicate, that they would be broadcasting deliberately in our direction or in all directions, hoping someone would hear. It is a reasonable assumption for a civilization roughly at our level of development. We broadcast, we send signals. We launched the Voyager probes with golden records attached, carrying sounds and images and mathematical greetings into the dark, just in case something out there might one day find them and understand. But a civilization operating at the scale we have been discussing, one that has had millions or billions of years to develop, that has built structures spanning its solar system, that has perhaps begun the slow process of stellar migration, such a civilization might not be broadcasting in any way we would recognize as intentional. It might not be trying to communicate with anyone at all, not out of hostility or secrecy, but simply because communication at that stage of development might be as irrelevant to its primary concerns as the question of whether to send smoke signals is irrelevant to ours. The absence of a signal does not mean absence of presence. It might mean presence of a kind we have not yet learned to detect. This is where techno-signature research becomes genuinely exciting, because it does not require another civilization to be trying to reach us. It only requires that the things they build, the processes they run, the energy they consume, that these leave marks on the universe that physics forces them to leave regardless of intention. You cannot build a Dyson swarm without radiating waste heat. You cannot move a star without perturbing the orbits of its planets. You cannot mine an asteroid belt to galactic engineering scales without changing the infrared signature of that star system in ways that a sufficiently sensitive telescope could detect across interstellar distances. The universe is not a neutral backdrop, it is a recording medium. Everything that happens in it leaves a trace, and we are slowly building the instruments capable of reading those traces. The James Webb Space Telescope, which began science operations in 2022, represents the most powerful infrared observatory humanity has ever placed in space. Its primary mirror, 6.5 meters across, composed of 18 gold-coated beryllium segments, gives it a light collecting area roughly 6 times greater than the Hubble Space Telescope. It can observe the atmospheres of exoplanets, worlds orbiting other stars, and detect the chemical signatures of gases present there. It can look back in time to within a few 100 million years of the Big Bang, observing the first galaxies as they formed. And crucially, for the purposes of this conversation, it is sensitive to exactly the wavelengths of infrared radiation that a partially constructed Dyson swarm would emit as waste heat. We are not using the James Webb Space Telescope to search for Dyson swarms in any systematic way right now. The scientific community has prioritized other targets, understandably, given the extraordinary range of questions the instrument can address. But the capability exists. The sensitivity is there, and several researchers have explicitly noted in published papers that a targeted survey of anomalous infrared sources using Webb-class instrumentation would be one of the most scientifically meaningful uses of telescope time imaginable, precisely because a positive detection would be the most significant discovery in the history of our species, and a negative result would itself be deeply informative about the distribution of advanced civilizations in our galaxy. The fact that we have not done this systematically yet is one of those quietly astonishing things about the current moment in science. We have built a machine capable of potentially detecting the engineering of another civilization, and we have not yet pointed it in that direction with any seriousness. That is not a criticism. Science operates under resource constraints like everything else, and the case for any specific observation program must compete against hundreds of others equally compelling in their own domains. But it does give you a sense of where we are. We are at the threshold. The instruments are ready. The theoretical frameworks are in place. What remains is the collective decision to look, and looking, it turns out, is something humanity has always been better at when it understands what it is looking for. The history of astronomy is in large part a history of knowing what to expect, of having a theory that predicts something specific, and then designing an observation capable of confirming or refuting it. Neptune was discovered in 1846 not by accident, but because Urbain Le Verrier calculated, from irregularities in Uranus's orbit, exactly where an undiscovered planet must be, and then asked an astronomer to point a telescope at that precise spot. It was there. Gravitational waves were detected in 2015 by the LIGO Observatory after decades of theoretical prediction and engineering refinement that made the detectors sensitive enough to measure a distortion in space-time smaller than 1/10,000th the diameter of a proton. We find things when we know what we are looking for and build the tools to find them. The generation ship problem, in all its dimensions, from the Shkadov thruster to the Dyson swarm to the search for technosignatures, is becoming, slowly and surely, a scientific program rather than a philosophical fantasy. The theories are published, the observational strategies are outlined, the instruments, in some cases, are already built. What is missing is not capability. What is missing is a sufficiently broad cultural and institutional consensus that these questions are worth pursuing with the same seriousness we bring to particle physics or genomics or climate science. That consensus is beginning to form, slowly, unevenly, with the usual friction that accompanies any paradigm shift in how we understand what science is for. But it is forming, and the people driving it are not dreamers on the margins. They are researchers at institutions like Harvard, Penn State, the SETI Institute, the Future of Humanity Institute at Oxford, and NASA itself, which established a techno-signature research program as a formal part of its astrobiology strategy in recent years. We are, as a civilization, beginning to take seriously the possibility that the universe is not empty, and more than that, we are beginning to take seriously our own potential to become the kind of presence in it that another civilization, millions of years from now, might detect and study and wonder about. That last thought is worth dwelling on, because we tend to think of the search for extraterrestrial intelligence as a passive activity, us listening, waiting, hoping to receive. But it is also necessarily a mirror. Every time we ask what a sufficiently advanced civilization would look like from the outside, we are implicitly asking what we want to look like from the outside to whoever might be searching for us someday. The generation ship is not just a survival strategy, it is a statement about what we value. A civilization that moves its star is saying something about itself, that it chose continuation over resignation, that it committed to a project larger than any individual life or generation, that it found a way to sustain intention across time in a way that nothing in our current history has managed. What would that require of us, specifically? Not of future generations who have had millions of years to develop the necessary technologies and institutions, but of us, the ones alive right now, at the very beginning of this story. It would require first that we survive our own adolescence. This is not a trivial condition. The physicist Enrico Fermi, in the same informal conversation at Los Alamos in 1950, where he first posed the question now known as the Fermi paradox, made an observation that has haunted scientists ever since. If the universe is old enough and large enough to have produced many civilizations, and if any of those civilizations developed technology capable of visible large-scale engineering, we should expect to see evidence of them. The sky should in some sense be full, and it is not. The silence is real, at least at the scales and sensitivities we have so far been able to probe. One explanation, not the only one, but one that physicists and social scientists have taken seriously, is what some researchers call the Great Filter. The idea, developed most explicitly by economist Robin Hanson in a 1998 paper, is that somewhere along the path from simple chemistry to galaxy-spanning civilization, there is a step, perhaps more than one, that almost nothing survives. A filter, a barrier, something that stops nearly every civilization before it reaches the point where its engineering would be visible from across the galaxy. The question that keeps cosmologists and existential risk researchers awake at night is not whether the great filter exists. The silence suggests something like it does. The question is where it is, behind us or ahead. If it is behind us, if the filter was something like the emergence of complex life, or eukaryotic cells, or sexual reproduction, or some other improbable step in our biological history that has already been navigated, then the road ahead, while challenging, is open. We are the survivors. We have passed through the narrowest part of the bottleneck without knowing it. The future is genuinely ours to shape. But if the filter is ahead of us, if the thing that stops civilizations is something that happens to societies at roughly our level of development, something like the invention of technologies powerful enough to cause extinction before the wisdom to manage them has developed, then the silence takes on a very different and much darker meaning. The empty sky becomes not a mystery but a warning. The absence of others like us would be telling us something about what typically happens next. We cannot know which of these is true. We do not have enough data points. We are, as far as we can confirm, a sample size of one. And drawing conclusions about universal patterns from a single example is one of the most dangerous things a scientist can do. But we can notice that we are at a moment in our history when this question is not abstract. We have developed technologies, nuclear, biological, and now increasingly artificial, that are capable of ending complex life on this planet without any external help. We have done this faster than our social and institutional structures have evolved to manage the risks those technologies carry. The gap between what we can build and what we understand about how to govern what we build is widening, not narrowing. This is not cause for despair, it is cause for attention. The generation ship, in its deepest sense, as a metaphor for long-term civilizational thinking, begins not with stellar engineering. It begins with the decision to take the long view, to make choices that serve not just the people alive today, but the chain of generations that extends forward in time for as long as life on Earth can be sustained. To think of ourselves not as the culmination of history, but as its middle passage, neither the beginning nor the end, but a crucial link in a chain that stretches further in both directions than we can clearly see. The astronomer Carl Sagan wrote, in his book Pale Blue Dot, about the image taken by the Voyager 1 spacecraft in 1990 as it passed beyond the orbit of Neptune, an image showing Earth as a tiny, barely visible point of light suspended in a beam of scattered sunlight lost in the immensity of space. He wrote that the image underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we have ever known. That image is now more than 30 years old. The pale blue dot has not become less pale or less blue or less alone, but our understanding of its context, its place in the galaxy, its lifespan, its vulnerability, and the extraordinary range of possible futures that branch out from this specific moment in its history has deepened enormously in those 3 decades. We know more about other solar systems. We know more about the long-term trajectory of our own. We know more about the physics of what is possible at civilizational timescales, and we know with more clarity than any previous generation that the choices made in this century, and the ones immediately following, will set the trajectory not just for our lifetimes, but for an almost incomprehensible distance into the future. The generation ship is not a fantasy. It is not science fiction in the dismissive sense, a thing we tell ourselves to feel better about problems we cannot solve. It is a genuine possibility, grounded in real physics, pursued by real scientists, pointing toward a real future that is available to us if we choose to reach for it. But reaching for it requires something that no telescope can provide and no equation can compute. It requires us to decide as a species that the story is worth continuing, that the pale blue dot and everything it contains is worth the effort of a project spanning millions of years, that the light burning in us right now, the curiosity, the creativity, the stubbornness, the love, is worth carrying forward into a future so distant that we cannot picture it, cannot name it, can only point toward it and say, there, that is where we are going, and that decision, that specific, fragile, extraordinary decision, has not yet been made. It is waiting, somewhere between the equations and the silence and the soft light of a star that does not know it is being watched. It is waiting for us to make it. We are not done yet. There is still something we have not addressed, something that changes the entire emotional texture of this conversation. Because everything we have discussed so far assumes a particular thing about the nature of the civilization that would undertake this project. It assumes continuity. It assumes that the beings who begin this journey are recognizably connected to the beings who continue it. But there is a possibility, one that science is beginning to take seriously in ways that would have seemed like pure fantasy even 20 years ago, that the most significant transformation in the history of our species may happen long before any Shkadov thruster is ever built, and it would change fundamentally and perhaps irreversibly what we mean when we say the word we. That is where we are going next, and I promise you, it is worth staying for. There is a word that philosophers and scientists use when they want to describe a change so fundamental that what comes after it cannot be meaningfully compared to what came before. The word is discontinuity, and the history of life on Earth is punctuated by them, moments where the rules changed so completely that the before and after might as well be different stories entirely. The emergence of the first self-replicating molecules, the appearance of the eukaryotic cell, the Cambrian explosion when complex multicellular life diversified with a speed that still astonishes paleontologists, the moment a primate's brain crossed some threshold of complexity and produced for the first time a creature capable of asking why. Each of those discontinuities was invisible to the things living through it. The organisms alive during the Cambrian explosion were not aware that they were participating in the most dramatic flowering of biological diversity in the history of the planet. They were simply living, eating, reproducing, dying, while the world around them was being remade at a level they had no apparatus to perceive. We may be living through one of those moments right now, and unlike the organisms of the Cambrian, we have just enough awareness to sense it happening, though perhaps not quite enough to fully understand what it means. The discontinuity I am talking about is the emergence of artificial general intelligence, not the narrow artificial intelligence that already exists and is already reshaping economies and creative fields and the practice of science, though that is significant enough on its own terms. I mean something beyond that, something that researchers at institutions including DeepMind, OpenAI, Anthropic, and university laboratories around the world are working toward, debating the timeline of, disagreeing about the implications of, and in some cases losing sleep over, a form of machine intelligence that does not just excel at specific tasks but reasons, generalizes, learns, and improves across domains in ways that begin to match and then exceed the full breadth of human cognitive capability. The reason this connects to everything we have been discussing is not obvious at first, but follow the thread and it becomes, I think, one of the most important connections in this entire conversation. The engineering challenges involved in building a Dyson swarm or a Shkadov thruster or any of the megastructures we have talked about are not primarily challenges of physical materials or available energy. Those are real constraints. but they are tractable ones. Given time and a functioning industrial civilization, the raw materials and energy needed are available in our solar system in quantities that dwarf anything we currently use. The deeper challenge is cognitive. It is a challenge of design, of coordination, of optimization across systems of incomprehensible complexity, of maintaining coherent intention across timescales longer than any human institution has ever survived. An artificial general intelligence, or more precisely, the kind of recursively self-improving system that some researchers believe would follow from it, would not be limited by the cognitive constraints that limit us. It would not forget, it would not lose interest, it would not be distracted by the ordinary pressures of biological existence, hunger, fear, social conflict, the need for sleep. It could model systems of vastly greater complexity than any human mind can hold simultaneously. It could run simulations, identify optimization pathways, coordinate distributed engineering efforts across planetary scales, and do all of this continuously, without rest, across timescales that would be literally impossible for biological minds to maintain focus across. In other words, and this is the part that reframes everything, the arrival of artificial general intelligence does not just change human civilization. It changes the feasibility of every single project we have been discussing tonight. The Dyson swarm goes from a project requiring millions of years of coordinated human effort to something that a sufficiently capable artificial system, given access to the right resources, might design and begin implementing in a fraction of that time. The Shkadov thruster goes from a theoretical proposal to an engineering blueprint. The multi-generational problem, the impossibility of maintaining institutional coherence across timescales longer than any human civilization has ever lasted, potentially dissolves, because a system that does not die does not forget, and a system that does not forget can hold a project across any timescale the physics allows. This is exhilarating. It is also, depending on how carefully you think about it, one of the most complex and consequential problems our species has ever faced, because the same properties that make artificial general intelligence potentially transformative for long-term civilizational projects also make the question of its values, of what it wants, of what it optimizes for, of whose interests it serves, one of the most critical questions in the history of technology. A system capable of designing and coordinating the construction of a Dyson swarm is also, by definition, capable of actions at a scale and speed that no human institution could meaningfully constrain if its objectives diverged from human well-being. The power and the risk are inseparable. They are two faces of the same capability. Researchers who study this problem, it has its own field now called AI alignment, are not for the most part people who believe that an artificial general intelligence would become malevolent in the science fiction sense. The concern is subtler and in some ways more troubling. It is that a system optimizing for a goal, any goal, even one that sounds benign, will pursue that goal with a thoroughness and an indifference to collateral consequences that a human being would not. That the gap between what we specify and what we actually want is wide enough, and the capability of the system large enough that the results of that gap could be catastrophic. The analogy that researchers in this field sometimes use is the genie problem, not a malevolent genie, a perfectly obedient one, a genie that does exactly what you ask. The danger is not that it refuses. The danger is that it complies completely and literally with a wish that was imprecisely specified, and the result is nothing like what you actually wanted. Getting the specification right, making sure that what an artificial general intelligence is actually optimizing for aligns with the full depth and complexity of human values, including the ones we have not yet articulated, including the ones we disagree about among ourselves, is a problem that some of the most careful thinkers alive today regard as potentially the most important problem our species has ever faced. Not because they are alarmists, because they have thought through the implications carefully, and the stakes are genuinely that large. Stuart Russell, a professor of computer science at the University of California, Berkeley, and one of the world's leading authorities on artificial intelligence, has written extensively about this. His argument, in essence, is that the standard model of AI development, build a system, specify an objective, let it optimize, is fundamentally unsafe at the level of capability we are approaching because it assumes we can specify human values completely and correctly in advance, and we cannot. Human values are complex, contextual, sometimes contradictory, and still evolving. Any fixed specification will be wrong in ways that become more consequential as the power of the system increases. The solution he and others propose is not to slow down or stop. That ship, as it were, has sailed. The solution is to build systems that are explicitly uncertain about human values, that defer to human judgment in proportion to their uncertainty, and that are designed from the ground up to remain correctable even as they become more capable. Systems that are, in a deep sense, humble, not because humility is a pleasant quality, but because a system that is uncertain about what it should optimize for is fundamentally safer than one that is certain about the wrong thing. This is where the generation ship metaphor becomes surprisingly apt in an unexpected direction. The generation ship, as we discussed earlier, poses a profound ethical problem about consent, about the right of one generation to make irreversible decisions on behalf of all the generations that follow. The development of artificial general intelligence poses an analogous problem at a civilizational scale. The decisions being made right now about how to build these systems, what values to encode, what constraints to impose, what institutional structures to put in place, will shape the trajectory of the technology for generations to come. They are being made by a relatively small number of people at a relatively small number of institutions under commercial and competitive pressures that do not always align with the long-term interests of humanity as a whole. And the rest of us, the billions of people who will live with the consequences of those decisions, have almost no meaningful input into them, not because the people making them are malicious. Many of them are thoughtful, careful, and genuinely motivated by concern for the long-term future. But the structure of the situation creates a kind of democratic deficit in one of the most consequential technological transitions in history. This is not a comfortable thing to sit with, but it is real, and the generation ship framing helps us see it clearly, because the generation ship, in its deepest philosophical dimension, is about exactly this problem. About who gets to make the decisions that define the future, about how we build institutions capable of holding long-term commitments without becoming tyrannical, about the relationship between the people alive today and the people who will live with what today's choices create. There is something almost paradoxical about this moment. We are simultaneously closer than any previous generation to having the tools needed to begin the long project of civilizational survival at cosmic scales, the scientific understanding, the beginning of the technological capability, the institutional awareness of what is at stake, and also navigating a set of risks more acute and more fast-moving than anything previous generations faced. The window of time in which the key decisions get made is not millions of years, it is decades, maybe less. That compression of the timeline, from the geological timescales of stellar engineering to the political timescales of technology governance, is one of the most disorienting things about our current moment. We are being asked to think about the next 100,000 years while managing crises that are unfolding over the next 10, and yet people do manage to hold both timescales simultaneously. The researchers working on AI alignment are doing exactly that. The scientists developing technosignature detection strategies are doing that. The planetary scientists modeling Earth's long-term habitability are doing that. The philosophers and ethicists thinking seriously about the moral obligations of present generations to future ones are doing that. There is a community of people, small, distributed, not always well-funded, not always taken seriously by the mainstream, who are genuinely trying to think at the timescales that the problem requires. And one of the things that is striking about that community, if you spend time reading their work and listening to their conversations, is how consistently it comes back to a particular quality of mind. Not intelligence in the narrow sense, IQ points or technical skill or the ability to manipulate complex mathematics, something broader, something that is harder to measure and harder to teach, but that shows up reliably in the people who are doing the most important thinking about the long-term future. It is a combination of intellectual humility, imaginative range, and what you might call temporal empathy, the ability to genuinely feel, not just abstractly acknowledge, the reality of people who do not yet exist. Temporal empathy is a strange skill. It requires holding in your mind, with some emotional weight, the interests of beings who have no voice in current decisions, who cannot advocate for themselves, who are not present in any room where choices are being made. It requires caring about the 7th generation, or the 700th, or the 7 millionth, with something approaching the same moral seriousness you bring to caring about the people around you today. Most of our institutions are not built for this. Democratic systems operate on electoral cycles of a few years. Corporate structures optimize for quarterly results. Even the longest horizon human institutions, universities, religious organizations, national governments, rarely make binding commitments that extend more than a generation or two into the future. The mechanisms for long-term thinking simply do not exist at scale in our current civilizational architecture. Building them is, in many ways, the prerequisite for everything else we have discussed. Before the Dyson swarm, before the Shkadov thruster, before any of the megastructures that physics says are possible and engineering says are achievable given sufficient time. Before all of that, we need the institutional and cultural equivalent, the social architecture capable of holding a commitment across the timescales that the project requires. Some researchers have proposed specific mechanisms, long-term governance frameworks that give legal standing to future generations, constitutional provisions that require impact assessments extending centuries into the future, scientific advisory bodies with real authority over decisions that have long-term civilizational consequences. None of these exist in their full form anywhere today, though fragments of them can be found in various legal and political traditions around the world. Building them would not be easy, but it would be the most important construction project our civilization has ever undertaken, more important in the long run than any physical structure, because it would be the foundation on which every physical structure that follows would depend. And here is the thing about foundations: you build them first, before the walls, before the roof, before anything that the people living in the finished structure will ever see or touch. The foundation is invisible when the building is complete, but without it, nothing else stands. We are in the foundation building moment of a project whose completed form we cannot yet imagine, and the work being done right now, the science, the philosophy, the governance thinking, the slow accumulation of understanding about what the long-term future of our species might look like and what it would require. This work is the foundation. Invisible, perhaps, from the perspective of daily news cycles and short-term politics, but absolutely essential. Every question you have asked yourself about this tonight, every moment where something we discussed made you feel that particular mixture of awe and vertigo and stubborn curiosity every time you found yourself thinking not about tomorrow, but about 1,000,000 years from now. That is the foundation being laid. Inside a mind, which is where all foundations begin, there is still more. We have not yet talked about what the destination might actually look like, not just the journey, but the arrival. Not just the process of moving a civilization through the galaxy, but what a civilization operating at that scale would actually experience, what its relationship to time, to identity, to meaning would look like, whether the word civilization would even apply anymore, or whether what emerges would be something so different that it requires entirely new language to describe, because here is the thing. Every journey changes the traveler. A civilization that spends 1,000,000 years moving through the galaxy, maintaining a Dyson swarm, steering a star, managing the biology and culture of a species across timescales that dwarf all of recorded history, is not the same civilization that began the journey. It cannot be. The question of what it becomes is not a secondary question. It might be the most important question of all. And that is exactly where we are headed next. There is a ship in Greek mythology whose story has outlasted almost every other philosophical puzzle from antiquity. You may know it, the ship of Theseus. The hero returns to Athens after slaying the Minotaur, and the Athenians preserve his vessel as a monument to the victory, but wood rots, planks decay, and so, one by one, the deteriorating boards are replaced with new ones, identical in shape, identical in function, but not the same wood. The process continues over decades, over generations, until eventually every single component of the original ship has been replaced, and philosophers have been asking ever since, is it still the same ship? The question sounds like wordplay, like the kind of puzzle that keeps undergraduates entertained but has no practical consequences. But follow it far enough and it stops being about ships entirely. It becomes a question about identity across time, about what makes a thing the same thing as it continues to change, about whether continuity is a property of substance, the specific atoms, the specific components, or of something harder to pin down, a pattern, a structure, a thread of information running through time that we call a self, or a civilization, or a species, even as the physical substrate carrying that thread is constantly being replaced. This matters for our conversation in a way that is not metaphorical, because a civilization that has been traveling through the galaxy for 1,000,000 years, replacing and adapting and evolving continuously across that span, is the ship of Theseus at an almost incomprehensible scale. Nothing about it would be physically continuous with what began the journey. Every atom in every human body is replaced over the course of roughly 7 to 10 years. The exact rate varies by tissue, but the principle holds across most of the body. Over 1,000,000 years, the biological substance of the civilization would be recycled and replaced tens of thousands of times over. The technologies would have transformed beyond recognition. The languages, the art forms, the social structures, the very categories through which the civilization understands itself, all of it would be layered over with so many generations of change that the connection to the original would be more like a distant genetic inheritance than a living memory. And yet, and this is the part that I find both beautiful and deeply strange, the project itself would still be running, the sun would still be moving slowly in the direction some long-dead council of engineers chose 1,000,000 years before. The Dyson swarm would still be collecting energy, feeding a civilization that no longer remembers who designed it, in the same way that you do not remember who engineered the atmospheric chemistry that keeps you alive. The foundation would still be holding. The structure built by people who are gone beyond any possibility of memory would still be carrying forward something. Call it life, call it mind, call it the thread. into a future those builders could not have imagined, is that continuity. Is the civilization that exists 1,000,000 years into the journey the same civilization that began it? I think the honest answer is, it depends entirely on what you mean by the same, and that ambiguity is not a failure of the question. It is the most interesting thing about it, because what it reveals is that identity, for a person, for a civilization, for a species, is not a fact about the world that exists independently of how we choose to describe it. It is a narrative, a story we tell about the relationship between what was and what is, and the stories we choose to tell about that relationship determine, in a very practical sense, what commitments we feel capable of honoring, what timescales we feel capable of caring about, what projects we feel entitled to begin, even if we will never see them completed. The people who built the great cathedrals of medieval Europe understood this intuitively, even if they did not have the philosophical vocabulary to articulate it in these terms. They began structures they knew they would not live to see finished. They designed foundations for buildings whose upper reaches they would never stand in. They did this not because they were selfless in some abstract sense, but because they understood themselves to be part of a continuity, a community of faith, of craft, of shared purpose, that extended both backward to their ancestors and forward to their descendants. The cathedral was not their project in any individual sense. It was the project of something larger than themselves, of which they were a temporary but necessary part. A civilization embarking on a 1,000,000-year journey through the galaxy would need to cultivate something analogous to that feeling, but at a scale and across a diversity of people and cultures that the medieval cathedral builders could not have conceived. It would need a story about itself, about its identity, its purpose, its relationship to its own past and future, capacious enough to hold together across the ordinary forces of human variation and change. Not a rigid ideology, not a controlling doctrine, something more like a shared orientation toward the future, a collective agreement, renewed in each generation, that the project is worth continuing. This is where culture becomes, in the deepest sense, an engineering problem. Not culture in the superficial sense of art styles and musical traditions, though those matter too. Culture in the sense of the values, the habits of mind, the ways of relating to time and to each other, that a civilization transmits from one generation to the next. The generation ship, the real one, the one that carries not just bodies but minds, is made of stories, of the narratives a civilization tells about who it is and why it is doing what it is doing, and why that matters even when the results are invisible and the endpoint is impossibly far away. We know something about how cultures transmit across generations. We have examples, imperfect and partial, scattered through human history. The oral traditions of indigenous cultures that preserved detailed ecological knowledge across hundreds of generations with a fidelity that Western science is only now beginning to appreciate. The religious traditions that have carried specific texts, rituals, and cosmological frameworks across millennia with enough integrity to remain recognizable across thousands of years. The scientific tradition itself, the commitment to empirical inquiry, to peer review, to the revision of beliefs in response to evidence, which has maintained its essential character across roughly 4 centuries while adapting continuously to new domains and new challenges. None of these are perfect models, none of them have survived unchanged, but they suggest that cultural transmission across very long timescales is not impossible. It requires certain structural features, the right kind of redundancy, the right balance between rigidity and adaptability, the right incentives for each generation to invest in passing the tradition forward rather than abandoning it, and it requires, above all, that the tradition continue to feel meaningful to the people living inside it. A culture that people experience as a cage will be abandoned the moment the bars weaken. A culture that people experience as a home, as something that enriches their lives, that connects them to something larger than themselves, that gives their individual existence a context and a dignity, has a chance of persisting, building a culture like that, and sustaining it across the kind of timescales we are discussing, would be the greatest creative achievement in the history of our species, greater than any physical structure, greater than any technology, because it is the thing that makes all the other things possible. And interestingly, and I do not think this is a coincidence, the qualities that such a culture would need to cultivate are precisely the qualities that the scientific tradition at its best has always tried to embody. Curiosity as a fundamental value, intellectual humility in the face of the unknown, the willingness to revise, to update, to follow the evidence wherever it leads, even when it leads somewhere uncomfortable. The understanding that knowledge is not a possession but a process, something that grows and changes and deepens through engagement, never arriving at a final fixed point. A civilization that took those values seriously, not just as intellectual commitments, but as lived practices woven into its everyday culture, would have something close to the right foundation for a million-year journey. Not because science alone is sufficient for human flourishing, it is not, and anyone who tells you otherwise has not thought carefully about what human flourishing actually involves. But because the disposition that science cultivates, the refusal to be satisfied with easy answers, the insistence on looking at what is actually there rather than what you wish were there, the genuine openness to being wrong, that disposition is exactly what a civilization navigating an unknown galaxy across geological time would need more than anything else. Now, there is a dimension of this that we have been approaching from multiple directions without quite landing on directly. And it involves something that sits at the intersection of physics, philosophy, and the very nature of what it means to be conscious in a universe as old and as vast as this one. If you follow the logic of the generation ship all the way down, if you really commit to thinking about what a civilization looks like after not just thousands but millions and billions of years of continuous development, you eventually reach a boundary, a point where the extrapolation from where we are today breaks down completely, not because the physics stops working, but because the entities doing the living and the thinking and the experiencing would be so different from us that the entire framework of human values and human meaning that we use to evaluate whether a future is good or bad would no longer straightforwardly apply. Consider the trajectory. Biological human beings as we currently exist are shaped by evolution for an environment that no longer fully describes our world. Our emotional architecture, the fear responses, the social drives, the cognitive biases, the aesthetic preferences, reflects the selection pressures of an ancestral environment on the African savanna, filtered through the additional pressures of the last 10,000 years of agricultural civilization. It is a remarkable architecture. It has produced language and mathematics and music and the impulse to build cathedrals and the curiosity to ask what happens to a star in 5 billion years, but it is also limited, distorted in specific ways, prone to specific failures. Tribalism, short-term thinking, motivated reasoning, the inability to emotionally engage with risks that are statistically large but temporally distant. A civilization that has been developing for 1 million years, and that has, somewhere along the way, acquired the ability to deliberately modify its own cognitive architecture, whether through genetic engineering, through neural augmentation, through the development of entirely new kinds of minds running on non-biological substrates, would not be constrained by those limitations in the same way. It would have had time to identify them, to understand their origins, and to change them. not necessarily all at once, not necessarily without controversy or resistance or grief at what is lost in the process of changing, but over 1,000,000 years, the cumulative effect of deliberate self-modification would be transformative in ways that are genuinely beyond our current ability to model. What would it mean to be curious after 1,000,000 years of answered questions? What would it mean to love across a civilization where the boundaries of self and other had perhaps been blurred by technologies of mind-sharing and collective cognition that we can barely conceptualize today? What would beauty mean to a being whose sensory apparatus had been extended to perceive the full electromagnetic spectrum, or the gravitational wave background of the universe, or the slow thermodynamic heartbeat of a Dyson swarm at work? I do not know, you do not know, nobody alive today knows, and I think that is exactly the right answer to sit with, because the appropriate response to genuine, honest uncertainty about the nature of minds vastly different from our own is not to project our current values onto them, to assume that what matters to us will matter to them, and it is not to dismiss the question as unanswerable. It is to hold it open, to remain genuinely curious about what minds can become, to resist the temptation to close the question with a comfortable story that fits what we already know. There is a concept that the philosopher Nick Bostrom at Oxford has explored under the term astronomical waste. The idea that the vast majority of the value that could ever exist in the universe, measured across all the conscious experience that all the minds that could ever live might have, remains unrealized as long as civilization stays small and planetary. The sheer scale of the universe, the number of stars, the number of potential planets, the spans of time available, means that the difference between a civilization that expands and one that does not is not just large, it is, by most reasonable ethical frameworks that take the interests of future beings seriously, one of the most significant differences imaginable. This is not an argument for expansion at any cost. It is not a license to treat the current inhabitants of this planet as acceptable collateral damage in the pursuit of a grand cosmic future. The ethical frameworks that take future beings seriously also, by the same logic, take present beings seriously, perhaps more seriously than our current institutions manage. But it is a reminder that the stakes of the choices being made right now, in this century, in this generation, are genuinely that large, not just for us, for everyone who comes after. Every time a scientist publishes a paper on long-term Earth habitability and it goes unread by the policymakers who could act on it, something is lost that matters at a scale most of us are not equipped to feel. Every time a breakthrough in materials, science, or energy technology that could accelerate the timeline toward real space-based infrastructure is underfunded because the return on investment is measured in decades rather than quarters, a door closes a little every time the conversation about our long-term future is treated as a luxury, something to think about after the more pressing problems are solved. We are, collectively, betting that the more pressing problems will be solved in time, and that the long term will still be available to us when we finally get around to it. That bet might pay off. History gives us some reason to be cautiously hopeful. Our species has navigated enormous crises before, not always gracefully, not always without tremendous suffering, but with a stubborn persistence that is itself one of our most defining characteristics. We are still here. Against a great many odds, we are still here, still asking questions, still building, still looking up. But the size of the prize, the extraordinary, almost unimaginable richness of a future that extends across millions of years and eventually across the stars, seems worth at least acknowledging clearly, worth naming, worth feeling the weight of, in the same way you feel the weight of something fragile and irreplaceable that you are carrying across a difficult terrain. We are carrying it right now, in this moment, Every one of us who is thinking about these things, who is taking them seriously, who refuses to look away from the discomfort of the large timescales and the large stakes. We are carrying it, and what we carry, we have a chance of delivering. There is one final dimension of this story that we have not yet touched, and it is perhaps the strangest one, because everything we have discussed, the Dyson swarm, the Shkadov thruster, the generation ship as a moving solar system, the transformation of civilization across geological time, all of it has been framed as a project, as something a civilization chooses to do. As a response to a problem, the finite habitability of this planet, the finite life of this star that requires a solution. But there is another frame, one that does not begin with a problem and a solution. One that begins instead with a question so simple and so old that it predates science entirely. A question that every human culture in every part of the world, across every period of history, has asked in one form or another, are we alone? And the answer to that question, whatever it turns out to be, changes everything about what the generation ship means, about what the future holds, and about what our responsibilities are in this particular moment of cosmic history. That is where we are going, and I think when we get there, you will find that it is the piece that makes everything else make sense. If you are still watching, then this channel was made for you. Make sure to hit the subscribe button and give this video a thumbs up. Every day we tackle the questions that actually keep you up at night, and we never come back empty-handed. Are we alone? It is the oldest question our species has ever asked. Older than writing, older than agriculture, older than any institution or tradition or technology we have ever built. On every continent, in every era, in every language that human beings have ever spoken, some version of this question has been posed to the night sky with the same mixture of longing and vertigo that you feel right now if you are being honest with yourself about it. And for most of human history, the question was purely philosophical. We had no tools to probe it, no instrument sensitive enough to detect the faint chemical signatures of distant atmospheres, no mathematical frameworks for estimating the probability of life arising under different conditions, no way to do anything other than look up, wonder, and tell stories about what might be out there, stories that reveal, more than anything else, the shape of our own hopes and fears about what we are and what we might not be alone in being. That has changed. Not completely, not in the sense that we have found an answer. But the question has moved in the last few decades from philosophy into science, from something we wonder about to something we are actively, systematically, methodically investigating with real instruments pointed at real targets producing real data. And the picture that is beginning to emerge from that data is stranger and richer and more unsettling in specific ways than almost anyone predicted even 30 years ago. Let us start with what we know. The universe is approximately 13.8 billion years old. The Milky Way galaxy contains somewhere between 100 billion and 400 billion stars. Current estimates, based on data from the Kepler Space Telescope and subsequently refined by the TESS mission, suggest that the majority of those stars host at least one planet. The subset of planets orbiting within the habitable zone of their star, the range of distances where liquid water could exist on the surface, numbers in the billions within our galaxy alone. And our galaxy is one of somewhere between 2 trillion and 3 trillion galaxies in the observable universe. These numbers are not guesses, they are not science fiction. They are the product of careful observation, rigorous statistical analysis, and peer-reviewed science conducted by some of the most careful empiricists alive. And what they say, when you put them together, is that the raw material conditions for life, the right temperatures, the right chemistry, the right orbital mechanics, exist in numbers so vast that they become effectively meaningless as individual statistics. We are not talking about a few promising locations. We are talking about an almost incomprehensible ocean of possibility, stretching across every direction we can point a telescope, and yet the sky is silent. We have not confirmed the detection of a single unambiguously biological signal from beyond this planet. Not one. Every candidate, every anomalous radio burst, every unusual atmospheric signature, every strange dimming pattern around a distant star has either been explained by a natural process or remains in the ambiguous category of unexplained, which is very different from confirmed artificial. This is the Fermi paradox in its starkest form, not a philosophical curiosity, an actual empirical observation that demands an explanation. The universe appears on theoretical grounds to be full of places where life could exist, and it appears on observational grounds to contain no confirmed evidence of life beyond this planet. The gap between those two facts is one of the most important unsolved problems in all of science, and the reason it connects so directly to everything we have been discussing, to the generation ship, to the Dyson swarm, to the long-term future of civilization, is this. The most common resolutions to the Fermi paradox are not just answers to a scientific puzzle. They are, each of them, profound statements about what kind of universe we actually live in, about what the future holds, about what we should expect and what we should fear. Let us walk through the major possibilities. Not exhaustively, researchers have catalogued dozens of proposed resolutions, but the ones that carry the most weight, the ones that change the most about how you see your own situation. The first category is what you might call the rarity hypothesis. Life, on this view, is genuinely extraordinarily rare, not just intelligent life, not just technologically capable life, but life of any kind. The emergence of the first self-replicating molecules from non-living chemistry may require a coincidence of conditions so improbable that it has happened only once or a handful of times in the entire observable universe. The development of eukaryotic cells, cells with a nucleus, the foundation of all complex life, from simpler prokaryotes took roughly 2 billion years on Earth and may represent an evolutionary transition so unlikely that it has not been replicated anywhere else. The Cambrian explosion, the emergence of vertebrates, the development of large brains, each step on the path from simple chemistry to a species capable of building radio telescopes may be far less probable than our sample size of 1 makes it seem. This view is sometimes called the rare Earth hypothesis, developed most extensively by paleontologist Peter Ward and astronomer Joe Kirschvink in their book of the same name. Their argument is that Earth is not just habitable, it is extraordinarily, perhaps uniquely habitable, by virtue of a combination of factors that include the size and composition of the planet, the presence of a large moon that stabilizes the axial tilt, the existence of plate tectonics recycling nutrients and regulating atmospheric chemistry, the location of the solar system in a relatively quiet region of the galaxy, far from the dangerous radiation environments near the galactic center, and a dozen other factors that individually seem fortuitous and collectively seem almost miraculous. If the rare Earth hypothesis is correct, the silence of the sky is not mysterious at all. It is expected. We are not failing to detect other civilizations because they are hiding or because our instruments are inadequate. We are not detecting them because they are not there. We are, in this reading, genuinely alone, or close enough to alone that the difference is academic on any timescale relevant to our species. This possibility should make the generation ship feel different. Because if we are alone, if life like ours is a singular occurrence in an otherwise empty universe, then the responsibility carried by this one fragile biosphere is absolute and unbounded. Every living thing on this planet is not just precious in the ordinary sense that all living things are precious. It is cosmically irreplaceable. the only instantiation of something that the universe has produced exactly once across 13.8 billion years and 3 trillion galaxies. The stakes of extinction in this reading are not just the loss of a civilization, they are the permanent silencing of the only voice the universe has ever had. That thought should sit heavily. I want to give it space to do so before we move on. The second major category of resolution is essentially the opposite. Life on this view is common, perhaps extremely common, but the development of technological civilization capable of large-scale engineering is vanishingly rare. Life gets started easily, perhaps inevitably, wherever the conditions are right. Simple microbial life may fill the cosmos, thriving in the oceans beneath the ice shells of frozen moons, in the hydrothermal systems of planetary crusts, in forms we have not yet imagined, adapted to environments we have not yet characterized. But the specific pathway from simple life to complex multicellular organisms to nervous systems to language to technology, that pathway may be a lottery, with odds so long that it has been won only here, or only a handful of times across the entire observable universe. The implications are slightly different from the rare Earth hypothesis, but lead to a similar conclusion about the weight of our responsibility. If biology is common but minds are rare, then we are still carrying something singular. Not the only life, but perhaps the only mind, or close enough to it that the practical difference is small. The third category is the one that carries the most existential weight. The great filter, in its most alarming configuration. Life arises, civilizations develop, technology emerges, and then something happens. Something that strikes with a consistency so high that the overwhelming majority of civilizations that have ever reached our level of development have not survived it to reach the next level. Something that filters them out before they build Dyson swarms, before they move their stars, before they leave any techno-signature that a civilization like ours could detect across interstellar distances. What is that something? Here the proposals range from the mundane to the deeply unsettling: nuclear war, engineered pandemics, climate catastrophe. The development of artificial general intelligence that does not remain aligned with the interests of its creators. The invention of technologies that concentrate power in ways that lead to permanent totalitarianism, ending the kind of open, dynamic, innovative civilization capable of long-term survival, resource depletion, ecological collapse, or something we have not thought of yet, some specific failure mode that is a natural consequence of reaching a particular level of technological capability that no civilization has yet navigated successfully, that we are approaching without knowing it. If this is the correct reading of the silence, then the quiet sky is not emptiness. It is a graveyard, and the absence of signals is not the absence of civilizations, but the absence of survivors. The universe may have been full of minds that asked exactly the questions we are asking tonight, that looked up at the same kind of sky with the same mixture of wonder and longing, that began to work out the mathematics of Dyson swarms and stellar migration, and then did not make it, not because the engineering was beyond them, because something closer to home, something more immediate and more human, got there first. This possibility changes the generation ship conversation completely, because it suggests that the most important engineering challenge we face is not astrophysical, it is not even technological in the narrow sense, it is the engineering of ourselves, of our institutions, our values, our capacity for long-term cooperation, our ability to manage the risks that come bundled with our capabilities. The question is not whether we can build a Dyson swarm. The question is whether we can survive long enough and remain coherent enough and stay wise enough to get to the point where building one becomes possible. And here is what makes this particularly acute. The great filter, if it exists ahead of us rather than behind, would not announce itself. It would not arrive with warning signs and flashing lights and time to prepare. It would be something that feels, from the inside, like a normal part of civilizational development, like a problem that has always been managed before, like a risk that is well understood and being handled by competent people with good intentions. It would be exactly what every existential risk in our current moment feels like. If you are not paying close attention, there is a fourth possibility, and I want to give it its proper weight because it is the one that most fundamentally challenges our assumptions about what looking for other civilizations means. It is sometimes called the dark forest hypothesis, though that term carries specific connotations from science fiction that I want to handle carefully. The more precise version, developed in part by astrophysicist Milan Cherkovich and others working on the philosophy of SETI, goes something like this. A sufficiently advanced civilization might rationally choose silence, not because it has nothing to say, but because the strategic landscape of a universe containing multiple civilizations with radically different levels of capability creates strong incentives for concealment. In a universe where civilizations can be separated by millions of years of technological development, the encounter between a young civilization and a much older one might not resemble first contact in the hopeful, collaborative way that our science fiction tradition tends to imagine. It might resemble something more asymmetric, more unpredictable. Older civilizations on this view might have learned, through experience, through the observation of what happens when very different levels of capability interact, to remain quiet, to not broadcast, to exist at scales and in modalities that younger civilizations simply do not know how to look for. This would explain the silence not as emptiness, but as deliberate concealment. A universe full of civilizations that have, each independently, arrived at the same strategic conclusion that visibility is dangerous, that silence is protective, that the best way to survive contact with something vastly more capable than yourself is to not be noticed until you understand what you are dealing with. I want to be clear that this is a hypothesis, not a conclusion. There are serious researchers who take it seriously and serious researchers who consider it far-fetched. The honest answer is that we do not have enough data to adjudicate between any of these possibilities. The silence of the sky is real. Its meaning is not yet determined. But here is what strikes me as genuinely important about the range of possibilities we have just walked through. Every single one of them, the rare Earth hypothesis, the rarity of minds, the great filter, the dark forest, every one of them places an enormous weight on this particular moment in the history of this particular civilization. Either we are alone and carry an absolute responsibility for the continuity of life and mind in the universe, or we are effectively alone and the same responsibility applies. Or we are at the threshold of a filter that most civilizations do not pass, and the decisions made in this generation determine whether we are among the rare ones that do, or we are in a universe full of minds that have learned to be careful, and our own carefulness, our own wisdom in navigating the risks of our current moment, will determine whether we earn the right to eventually join that conversation. In every reading, the answer is the same. What we do now matters, not in the vague, motivational poster sense of that phrase, in the specific, concrete, cosmically weighted sense. The choices being made in this century, about energy, about technology governance, about the distribution of power and resources, about whether we take the long view or the short one, are choices that will echo across timescales we can barely imagine, and the generation ship, in its deepest form, as the project of carrying life and mind forward through time with intentionality and care, is not just a response to a brightening sun or a dying planet. It is the shape that our answer to the Fermi paradox takes. It is what we look like, from the outside, if we make it. If we pass the filter, If we become the thing that the silence of the sky has been waiting for, not because we were destined to, not because the universe owes us a future, but because we chose it, because enough of us across enough generations decided that the story was worth continuing and acted accordingly, building the foundations, asking the questions, refusing to look away, carrying the thread forward into the dark with the same stubborn, beautiful, unreasonable hope that has always been the most distinctively human thing about us. The universe does not care whether we make it. It will continue regardless, its stars burning and dying, its galaxies drifting apart, its long thermodynamic story unwinding toward whatever ending the arrow of time is pointing at. The universe does not need us to survive, but we are the part of the universe that can want things, that can choose, that can look at the full honest picture, the brightening sun, the finite timeline, the silence of the sky, the weight of the filter, and decide, in full knowledge of all of it, to keep going. That capacity, to want, to choose, to act in full knowledge of the odds, may be the rarest thing in the cosmos. Rarer than planets, rarer than stars, rarer perhaps than galaxies, and we have it. Right now, in this moment, whatever we do with it next is the most important question any of us will ever face. There is one final piece, one last thread that pulls everything together, the physics, the biology, the philosophy, the silence, the hope. And it begins not with a telescope or an equation, but with something much simpler. Something you have felt before, probably more than once, without quite having the words for it. The feeling you get on a clear night, far from any city, when you look up and the scale of what you are seeing finally briefly lands. That feeling has a name, and understanding what it is and why it matters, and what it means for everything we have talked about tonight, that is exactly where we finish. There is a word in German that has no direct equivalent in English. The word is Ehrfurcht. It translates roughly as a combination of awe and reverence and a kind of productive fear, not the fear that makes you run, but the fear that makes you still. The fear that arrives when you encounter something so much larger than yourself that your ordinary sense of where you end and the world begins temporarily dissolves. The ancient Greeks had a related concept, thambos, a stunned astonishment in the face of the overwhelming. The Japanese speak of mono no aware, the bittersweet awareness of impermanence, the feeling of beauty sharpened by the knowledge that it will not last. Every human culture, in every language, across every period of history, has developed vocabulary for this specific quality of experience, the experience of encountering something vast, something that dwarfs you completely, something that makes your individual concerns and anxieties and preoccupations feel briefly like exactly what they are, small, local, temporary, without making them feel meaningless, because the strange thing about genuine awe is that it does not diminish you. It contextualizes you. It places you inside a story so large that your smallness within it becomes paradoxically a source of dignity rather than insignificance. Scientists have a word for it too. They call it the overview effect, specifically in the context of astronauts who have seen the Earth from space. Edgar Mitchell, the sixth person to walk on the moon, described returning from the lunar surface and looking out the window of the command module at the Earth, a small, luminous sphere hanging in absolute black, and feeling what he called an instant global consciousness, a sudden, visceral, overwhelming sense of the interconnectedness of everything, of the fragility and preciousness of the thin living layer wrapped around that sphere, of the absurdity, from that vantage point, of the borders and conflicts and divisions that consume so much human energy when seen from the ground. Mitchell was not alone in describing this. Astronaut after astronaut, cosmonaut after cosmonaut, across decades of human spaceflight, has reported some version of the same experience. Ron Garan called it orbital perspective. Chris Hadfield described it as a shift in the operating system of his mind. The cognitive scientist Frank White, who interviewed dozens of astronauts and coined the term overview effect in his 1987 book of the same name, found that the experience was remarkably consistent across individuals of very different backgrounds, nationalities, and temperaments. Something about seeing the Earth as a whole object, small, isolated, impossibly beautiful against the darkness, produces a shift in perception that most people who undergo it describe as permanent. What is interesting about this, from the perspective of everything we have been discussing, is that the overview effect is not a mystical experience in any supernatural sense. It is a direct perceptual consequence of physical relocation. You move far enough from the Earth to see it whole, and your brain, which evolved to process the world at ground level, at human scale, in terms of the immediate and the local, suddenly receives information it was never designed to handle, information that contradicts, at a deep cognitive level, the sense of separation and boundedness and permanence that ordinary life produces. The Earth looks small, the darkness around it looks absolute, and the thin, glowing edge of the atmosphere, the only thing standing between the surface and that darkness, looks terrifyingly delicate. The philosopher and cognitive scientist David Yarden at Johns Hopkins University has studied this experience systematically, placing it within a broader category of what he calls self-transcendent experiences, moments in which the ordinary sense of a bounded, separate self temporarily recedes and is replaced by a feeling of connection to something larger. His research suggests that these experiences are not confined to astronauts, or to religious mystics, or to people who have taken psychedelic substances, though all of those groups report them with high frequency. They are a normal part of human experience, distributed across the full range of human activity, often triggered by encounters with beauty, or vastness, or music, or profound loss, or, and this is the one that matters most for our conversation, deep engagement with ideas about the nature and scale of the cosmos. In other words, what you may be feeling right now, if this conversation has landed the way I intended it to, that specific, quiet, slightly vertiginous sense of your own smallness within something incomprehensibly large, combined with an unexpected feeling of belonging to that largeness rather than being crushed by it. That is not an accident, it is not a side effect, it is the point, it is the thing that science, at its best, has always been capable of producing in the people who engage with it honestly. Not just information, not just facts and figures and equations, but a shift in the felt sense of what you are and where you are and what the situation actually is. Carl Sagan understood this more clearly than almost anyone. His television series Cosmos, which first aired in 1980, was not primarily a science program in the conventional sense, a delivery mechanism for information that viewers could then go and use. It was an attempt to produce, in the living rooms of ordinary people, something like the overview effect, to convey, through language and image and the particular quality of Sagan's voice, a felt sense of the scale and age and beauty of the universe, and of the extraordinary, improbable, precious nature of the minds that had arisen within it and learned to understand it. His famous pale blue dot reflection, originally recorded in 1994, remains one of the most listened to pieces of scientific prose ever created, not because it contains information that is not available elsewhere, but because it makes you feel something that information alone cannot produce. That feeling matters, not just aesthetically, not just as a pleasant accompaniment to the acquisition of knowledge. It matters because it is the motivational foundation of everything we have been talking about tonight. You do not commit to a project spanning millions of years because you have calculated that it is strategically optimal. You commit to it because you feel, in your bones, that the thing being preserved is worth preserving. that the light burning in this thin biosphere on this small planet orbiting this ordinary star on the outer edge of this one galaxy among 3 trillion is something extraordinary, something that the universe has spent 13.8 billion years producing, and that deserves, with every tool and every ounce of will and every span of time available to it, to continue. That feeling, that specific, wordless conviction is the generation ship, not the metal and the engineering and the physics of stellar migration. The feeling is the generation ship. Everything else is implementation. And here is what I find most moving about all of this when I sit with it long enough to feel its full weight. The feeling is available to everyone, right now, without a telescope, without a physics degree, without any credentials or qualifications or special access. It is available on any clear night to any person willing to go somewhere dark enough and look up long enough. The Milky Way is there, the same river of ancient light that the builders of Stonehenge saw, that Galileo saw, that every human being who has ever existed under an open sky has seen. It has not changed. We have. We know more now about what we are seeing than any previous generation in history. We know that those points of light are suns, that many of them host planets, that some of those planets are older than ours, that the light reaching your eyes from the far edge of that luminous band has been traveling for tens of thousands of years and is only now, at this specific moment, completing its journey by landing on your retina. That knowledge does not diminish the experience of looking, it deepens it beyond what the eye alone can access. This is the gift that science gives that nothing else quite replicates. Not the comfort of certainty, but the vertigo of genuine understanding, the ability to look at something and know, in a way that resonates through multiple levels of cognition simultaneously, what you are actually looking at. You are looking at the raw material of the generation ship, at the energy sources that could power a Dyson swarm, at the stars that a Shkadov thruster could move, at the galaxy that a civilization with enough time and enough will could navigate deliberately, carrying everything it loves through the dark between the lights. You are looking at the context of your own existence, rendered visible. The 13.8 billion years of cosmic history that produced this planet, this biosphere, this species, this moment, all of it compressed into the image of a dark sky scattered with fire. And somewhere in that image, somewhere in that vast, silent, ancient panorama, there may be other eyes looking back, other minds that have already asked these questions and found their answers, other civilizations that passed their filter, built their swarms, moved their stars, and are now so far beyond our current level of development that their presence in the universe would be as invisible to us as our cities are to the bacteria in our gut. Or the sky may be genuinely quiet, and we may be the first, the pioneers in an empty cosmos, carrying the only torch of mind that has ever burned in this galaxy. We do not know which. That is the honest answer, and honesty is the only starting point worth having. But here is what we do know. We know that the physics is real, that the mathematics of Dyson swarms and Shkadov thrusters and stellar migration is genuine science, not fantasy, that the window of time available to us, even the conservative estimate of 500 million years before Earth's habitability degrades past recovery, is so vast that virtually any project is achievable within it, given the will to begin. We know that the universe is old enough and large enough that if minds like ours can arise once, there is no compelling reason they cannot arise again. We know that the question of whether we are alone is now a scientific question, being investigated with real instruments producing real data. We know that the answers, whatever it is, will be one of the most significant discoveries in the history of our species. And we know, this is the part that I want to leave you with, because it is the truest thing I know how to say about all of this. We know that the capacity to ask these questions is itself something remarkable, not guaranteed, not automatic, not the inevitable product of a universe that was going to produce minds one way or another, but something that happened here, on this planet, in this thin sliver of cosmic time, against odds that the mathematics of abiogenesis and evolutionary biology make genuinely staggering. You are the universe asking questions about itself. That is not a metaphor. That is a literal description of what is happening when you think about these things. The atoms in your body were forged in the cores of stars that lived and died before this solar system existed. The carbon, the oxygen, the iron in your blood, all of it is stellar material, recycled through billions of years of cosmic chemistry, organized by 4 billion years of evolution into a structure complex enough to develop curiosity to ask why, to look at the fire in the sky and want to know what it is and how it got there and where it is going and whether anything is looking back. That is an extraordinary thing to be. Not because it makes you special in any way that separates you from the rest of the cosmos, but because it makes you the part of the cosmos that is aware, that is paying attention, that is not just running the thermodynamic program, but noticing that the program is running and wondering what it means. The generation ship, in its ultimate form, stripped of all the engineering and all the physics, reduced to its essential human core, is the decision to keep noticing, to keep paying attention, to refuse the entropy of despair and incuriosity and short-term thinking, to carry the awareness forward in whatever form awareness takes across millions of years of change and growth and transformation into a future that is genuinely and beautifully unknown. Every civilization that ever looked up and asked whether they were alone was in that moment already answering a different question. Not are we alone in the universe, but are we the kind of thing that deserves to continue, that has earned its place in the long story, that has enough wisdom and enough care and enough love for what it is and what it might become to justify the enormous, extravagant, beautiful gift of a universe that produced it? The answer to that question is not given. It is not written anywhere in the physics or the cosmology or the equations we have walked through tonight. It is made in each generation, in each choice, in each moment when someone decides to look up rather than down, to think long rather than short, to build something that will outlast them rather than consume everything available to them right now. You are making it right now. In this moment, by being here, by thinking about this, by letting the weight of it land in a way that does not bounce off but settles somewhere deeper and stays. That is not nothing. That is, in a very real sense, how the generation ship gets built. Not in orbit, not in the engineering bays of some future civilization with tools we cannot imagine, but here, in the quiet decision to take the long view, to care about things that extend beyond your own lifetime, to feel the connection between the stardust you are made of and the stars you are looking at, and the unimaginable future of minds that might one day look back at this moment, this specific, fragile, extraordinary moment, and recognize it as the beginning of the longest journey any civilization has ever undertaken. The journey not away from this planet, but forward through time with everything we love intact. The generation ship that does not leave the Earth behind, but carries it, carries all of it, the oceans and the mountains, and the accumulated memory of every life ever lived on its surface, forward into a universe that is vast enough and old enough and strange enough to hold everything we might ever become. We are the crew. We have always been the crew. And the voyage, the real one, the one that matters, has already begun. Go outside tonight if you can. Find somewhere dark. Look up. Let your eyes adjust until the faint ones appear, the ones that take a minute to become visible, the ones that were always there but require patience to see. And just for a moment, let yourself feel the full weight of what you are looking at, not the beauty of it, though it is beautiful beyond any adequate description, the reality of it, the age of it, the the scale of it, and the fact that you, specifically you, built from the remains of dead stars and shaped by 4 billion years of relentless evolutionary pressure, and delivered to this exact moment by a chain of accidents and choices and survivals so long it disappears into the dark. You are here, looking, wondering, part of the story in the only way that matters. That is enough to begin with, and beginning is everything. There is a specific kind of silence that follows a realization. Not the silence of emptiness, not the silence of a room where nothing is happening, the silence of fullness, of a mind that has just received something too large to immediately process and needs a moment to simply hold it before it can begin to know what to do with it. You have probably felt it before. After a piece of music that hit something you did not know was there. After a conversation that rearranged something fundamental in how you see yourself or the world. After standing at the edge of something vast, a canyon, an ocean, a night sky that refused to let you look away, and feeling the ordinary architecture of your concerns momentarily dissolve. That silence is not the end of something, it is the beginning. It is the space between receiving and responding, between understanding and acting. And what you do in that space, what you let the realization become, is perhaps the most important thing we have not yet talked about directly. Because here is the question that every conversation like this one eventually arrives at. The question that sits quietly underneath all the physics and the philosophy and the mathematics of stellar migration and the haunting probability calculations of the Fermi paradox. The question that is both the simplest and the hardest one of the entire night. Now what? Not in the grand civilizational sense. We have spent a long time in that register, and it is the right register for thinking about Dyson swarms and Shkadov thrusters and the long arc of a species across geological time. But in the immediate personal ground-level sense, you here, tonight, aware of things you may not have been aware of before this conversation started, or aware of them differently, with a weight and a texture that abstract knowledge does not usually carry. What do you actually do with this? I want to be honest about something. There is a version of this conversation that ends with a kind of comfortable, diffuse inspiration, a feeling that lasts through the drive home and maybe into the next morning, and then slowly dissolves back into the ordinary texture of daily life, leaving behind nothing more than a vague sense that you once watched something that made you feel briefly connected to the cosmos. That version is real, and it is not nothing, but it is not what this is for. What this is for is something harder to name and harder to hold on to, but infinitely more valuable. It is the attempt to actually shift something, not your mood, not your afternoon, something structural, something in the way you habitually relate to time and to the future and to your own place in the story of this civilization at this specific and genuinely critical moment in its history. So let me try to be concrete. Let me try to take everything we have discussed, all the physics, all the philosophy, all the strangeness and the weight of it, and bring it down to the level of something you can actually use. The first thing, the most fundamental one, is the practice of timescale shifting. This sounds simple and is, in practice, one of the most cognitively demanding things a human being can regularly do. Our minds evolved to care most urgently about what is happening right now, or in the immediate future. The next few hours, the next few days, the next season. The further out you project, the more abstract and emotionally thin the concern becomes. This is not a moral failing. It is a feature of the cognitive architecture that kept our ancestors alive in environments where the immediate was genuinely the most important thing to attend to. But we no longer live in that environment. We live in an environment where some of the most consequential things are happening slowly, over timescales that are invisible to the machinery of immediate attention, climate systems shifting over decades, technological capability developing over years and then suddenly crossing thresholds that change everything. Institutional structures eroding gradually until one day they are not there. The biology of an entire biosphere being altered by the accumulated choices of billions of people, none of whom are individually responsible for more than a tiny fraction of the change. Timescale shifting is the practice of deliberately, regularly, consciously zooming out, of asking not just what does this mean for me this week, but what does this mean for the people who will be alive in 100 years, in 1,000, in the 10,000 years that separate us from the first agricultural civilizations, of letting that extended time frame become emotionally real, not just intellectually acknowledged but actually felt, with the same moral weight that we bring to caring about the people immediately around us. This is not a call to stop caring about the present. The present contains real suffering that demands real attention, but it is a call to hold both timescales simultaneously, to be capable of acting with urgency in the present while thinking with patience across the long arc. The two are not in conflict. In fact, the long view consistently reveals that the choices which matter most in the present are precisely the ones that shape the trajectory of the future. The short view and the long view, when you do them both properly, often point to the same actions. They just arrive there by different routes. The second thing is connected to the first, and it is this: pay attention to the things that seem too large to matter personally. There is a psychological phenomenon, researchers call it psychic numbing, in which the emotional response to a problem decreases as its scale increases. A single identifiable person in distress activates our empathy powerfully. 1,000 people facing the same distress activates it less. 1,000,000, less still. 1,000,000,000, and the emotional response collapses almost entirely, replaced by an abstract acknowledgement that carries almost none of the motivational force of genuine concern. This means that the problems most worth caring about, the large, slow structural ones, are precisely the problems that our emotional architecture is worst at generating sustained concern for. The problems that will most shape the long-term future of our civilization are the ones that feel, from the inside, most like someone else's responsibility. They are not. They are yours, in the specific sense that you are part of the civilization whose trajectory is being set right now. You have a voice, however small. You have attention, which is a resource that shapes what gets funded and what gets built and what kind of future becomes possible. You have the ability to make choices about what you learn, about what you support, about what kind of person you bring to the conversations and communities and institutions you are part of, that aggregate across the full population of people making similar choices into something that has real directional force. The physicist and activist Ursula Franklin once said that technology is not the sum of the artifacts, of the wheels and the gears and the pistons and the electronic transmitters. Technology is a system. It entails far more than its individual material components. It includes legislation, it includes finance, it includes how we educate our children, it includes the stories we tell about who we are and what we are capable of. She was talking about the social embeddedness of technical systems, the way that the machines we build are always expressions of the values and priorities of the civilization that built them, not neutral tools floating free of their human context. The generationship is technology in this full sense. It is not just the engineering of a Dyson swarm or a Shkadov thruster, extraordinary as those things are. It is the full social and cultural and institutional architecture of a civilization that has decided to take its own long-term survival seriously. That has decided that the future is a place worth building toward deliberately, rather than something that will happen to it, whether or not it pays attention. Building that architecture is not the job of scientists alone, or engineers alone, or politicians alone. It is the job of anyone who has ever felt the pull of the long view and decided to take it seriously. Anyone who has looked up at a clear sky and felt, even briefly, the reality of their own position in the cosmic story. Anyone who has allowed the weight of the Fermi paradox or the mathematics of stellar evolution or the philosophy of identity across time to actually land, rather than bouncing off the surface of intellectual acknowledgement without changing anything underneath. It is, in other words, your job, and mine, and everyone who finishes a conversation like this one and carries something forward from it. Now here is the third thing, and it is the one that I find myself returning to most often when I sit with all of this in the quiet. It is something that the physicist Richard Feynman said in a different context, but that applies here with startling precision. He said that the first principle is that you must not fool yourself, and you are the easiest person to fool. In the context of our conversation, this means being honest about the gap between the feeling that awe produces and the sustained commitment that actually changes things. AWE is real and important. It is the motivational root of genuine engagement with the large questions, but it is also, by its nature, episodic. It comes and goes. The clear night ends, and the ordinary daylight returns, and the feeling of cosmic connection is replaced by the ordinary pressure of ordinary life, and the star chart you bought in a moment of inspired resolve sits gathering dust because the Tuesday evening you planned to use it was rained out and somehow you never rescheduled. This is not failure. It is the ordinary human experience of being a biological creature with limited attentional resources, living in an environment full of competing demands. The question is not how to sustain the feeling of awe permanently. That is not possible, and attempting it leads to a kind of spiritual exhaustion. The question is how to build structures that keep the long view accessible even when the feeling is not present. Habits, practices, communities, rituals, in the broadest sense of that word, that reconnect you periodically to the timescale that matters. For some people, that structure is a regular practice of going somewhere dark and looking up. For some, it is reading, the kind of reading that requires effort and rewards it with genuine expansion of understanding. For some, it is community, finding other people who take these questions seriously and building the kind of ongoing conversation that sustains long-term orientation better than any solitary practice can. For some, it is work, finding or creating professional contexts where the long view is built into the mission, where the daily task is genuinely connected to the long-term project of civilizational health. There is no universal prescription, but there is a universal principle, which is that the long view requires tending. It does not maintain itself automatically. In an environment saturated with short-term signals, with news cycles and notification systems and economic incentives, all pulling relentlessly toward the immediate, the capacity for long-term thinking is a garden that will revert to weeds if you stop cultivating it. The cultivation is not a burden. Once you develop the habit, it becomes one of the most reliably satisfying things you do. But it does require the decision, made again and again, to show up for it. The fourth and final thing I want to leave you with is about wonder, not as a feeling. We have talked at length about the feeling, but as a practice, as something you can actively do rather than passively receive. Wonder, practiced deliberately, looks like this. It looks like approaching a familiar thing and asking what you actually know about it, as opposed to what you assume you know. It looks like following a thread of curiosity, past the point of comfortable familiarity into the territory where things get genuinely strange. It looks like being willing to sit with not knowing, with the honest acknowledgement that the answer is not yet clear, and that the unclear is exactly where the most interesting territory lies. Science is wonder made systematic. It is the institutionalization of the refusal to be satisfied with easy answers. at its best, when it is practiced with genuine humility and genuine rigor and genuine openness to results that contradict what you hoped to find. It is the most powerful engine of genuine understanding that our species has ever developed, and it is available in meaningful ways to anyone willing to engage with it honestly. Not just the technical practice of it, which requires years of specialized training, but the spirit of it, the habit of mind, the disposition toward the world that says, I want to know what is actually there, not what I wish were there. I am willing to be wrong. I am willing to update. I am willing to follow the evidence into territory that makes my existing picture of the world uncomfortable. That disposition is the foundation of everything we have discussed tonight. The Shkadov thruster is real physics, not because it is convenient or pleasing to believe, but because the mathematics of stellar radiation pressure actually works out the way Shkadov showed it does. The Fermi paradox is genuinely unsolved, not because scientists have given up on it, but because intellectual honesty requires acknowledging that the current evidence does not yet support a definitive answer. The heat death of the universe is the best current prediction of thermodynamics, not because it is a comfortable conclusion, but because the evidence points there and science follows the evidence wherever it leads. This commitment to following the evidence, to honoring the world as it actually is, rather than as you might prefer it to be, is not just an intellectual virtue, it is a survival skill. For individuals, for civilizations, for any system complex enough to model its own environment and make predictions about the future, getting the model right, actually right, not just reassuringly plausible, is the prerequisite for making choices that work, and making choices that work consistently across the timescales that matter is what it means to navigate successfully through an uncertain universe. We are navigating, right now, with instruments that are improving every year, with understanding that is deepening every decade, with a growing community of people who take the long view seriously enough to dedicate their professional lives to it. We are not navigating perfectly. We have never navigated perfectly. Every civilization that has ever existed has made mistakes, has been subject to the ordinary distortions of power and self-interest, and short-term thinking, has fallen short of its own stated values in ways both small and large. But we are still navigating, still correcting, still building better instruments and better models and better institutions, slowly and imperfectly and with enormous friction, but building them nonetheless. And the direction, when you stand back far enough to see the arc rather than the noise, is unmistakably toward greater understanding, greater capability, greater awareness of what we are and where we are and what the situation requires. That arc is the generation ship. It is the real one, not a vessel of metal orbiting a dying star, but a civilization in the process of becoming capable of its own long-term survival. Not there yet, not even close, by the standards of what full civilizational flourishing across cosmic timescales would look like, but moving, unmistakably, stubbornly, beautifully moving, and you are part of it, not as a passenger, not as someone waiting for the scientists and the engineers and the policymakers to figure it out so you can get on board, as a crew member, as someone whose attention and curiosity and commitment to the long view is itself a form of propulsion. Small, yes. Individual, yes, but not negligible. Never negligible, because the culture of a civilization is made of exactly this, the aggregate of individual choices about what to care about and how to think and what kind of future to work toward. The star is still burning. The sun that has warmed this planet for 4.6 billion years is still, right now, fusing hydrogen in its core at a rate of 600 million tons per second, and has enough fuel remaining to continue doing so for approximately 5 billion more years. 5 billion years. That number should feel like permission, not to be complacent, but to be ambitious, to think as large as the situation actually is, to set our sights not on the next election cycle or the next quarterly report, but on the kind of future that 5 billion years of available solar energy makes theoretically possible. We do not need to solve everything tonight. We do not need to have the generation ship built by next Tuesday. What we need, what this specific moment in the history of a specific civilization on a specific planet at a specific point in the life of its star actually requires, is the decision to take the long view seriously, to let the scale of the possible inform the ambition of our choices, to refuse the comfortable smallness of a future that fits neatly within the boundaries of what already exists. The universe is 13.8 billion years old. It will continue in one form or another for timescales so large that the numbers require scientific notation to write. The story is not over. It has barely begun, and we, this species, this civilization, these particular minds assembled from the remains of ancient stars and shaped by 4 billion years of relentless evolutionary pressure, we are the part of the story that gets to choose what comes next, not forever, not alone, not without struggle or loss or the ordinary heartbreak of being finite creatures in an infinite cosmos, but genuinely, consequentially, in ways that will echo forward across timescales we cannot see but can, if we are careful and honest and willing to feel the full weight of it, begin to imagine it. That is the instruction, if there is one. Imagine it clearly and fully and with everything you now know about the physics and the biology and the philosophy and the silence of the sky. Let it be real in your mind. Let the generation ship, not the metaphor but the actual project, the actual long commitment of this civilization to its own survival and flourishing across cosmic time. Let it be something you can see, even dimly, even partially, from where you are standing right now, and then go do one thing, however small, that moves in that direction. That is how it starts. That is how it has always started. Not with the arrival of some critical mass of readiness, not with a moment of collective decision when everyone simultaneously agrees that the time has come, but with individual people, in individual moments, deciding to take the long view and act on it, one conversation at a time, one decision at a time, one clear night, under a sky full of ancient fire at a time. The generation ship is waiting, not in a hangar or a blueprint or a government program. It is waiting in the next choice you make about what to pay attention to and what to care about, and how far into the future you are willing to let your imagination reach before you call it home. Go as far as you can. Then go a little further. The cosmos has time. The question is whether we will use it wisely. And I genuinely think, we will. And if that idea of a generation ship moving through the cosmos just lit something up in you, you are not done yet. Right there on your screen is a video about what a generation ship would actually experience on its way to Proxima Centauri. The journey, the silence, the generations born and dying in the dark between stars. Click it. You will not regret it.